Hello and welcome to Sleepy Science. Tonight we'll loosen our grip on the obvious and drift through 30 gentle surprises. We'll feel how now is a heartbeat late. Notice time stretch differently across your own body. Let empty space show its quiet push and pull. And hold a teaspoon that secretly weighs a mountain. We'll watch your brain sketch the world before seeing it. Catch everyday things softly glowing. Float a magnet on invisible rails. Calm light to a standstill. And follow particles that slip through walls or freeze mid-change when watched. We'll let a single traveler paint a wave pattern. Pair two far things with a shared fate. Read the vacuum's weather. Listen to sound make a horizon. And cool atoms until motion becomes a whisper. We'll step into an expansion with no center. Share nows that don't quite agree. Feel the small warmth of erased bits. And meet memories that rewrite as you recall. We'll try on a self-stitched from many voices. Borrow a bird's compass. Watch leaves move energy with grace. And see simple rules bloom into cities and minds. We'll push a sail with sunlight. Wander a game tree larger than stars. Touch matter's spacious fields and sense a single grain of light. We'll remember that maps aren't the land. Stand anywhere and still be central, and wonder whether reality keeps its own code. If this kind of quiet curiosity helps you rest, settle in, breathe once, and let's begin. You never see now. You think you're meeting the world in real time, but what you actually meet is a carefully edited replay. A smoothed, stitched, slightly delayed premiere that your brain releases a few milliseconds after the scene has already changed. And once you realize this, the idea of now softens into something more like a curated present. A best-guess movie projected just behind reality's leading edge, while you sit in the front row believing it's live. The trick begins with simple biology. Light has to enter your eyes, get turned into electrical signals, travel along nerves, be pre-processed in relay stations, and finally blossom into patterns across visual cortex. And even with fast neurons, the full loop costs precious tens to hundreds of milliseconds, which is long enough that if your perception were a clock, it would always be a fraction of a second late. Long enough that what you call the present is already the past. Yet somehow it still feels immediate because your brain refuses to simply wait. It predicts, smooths, and retrofits experience so the delay disappears. Like a film editor cutting out the choppy frames. You can catch the edit if you know where to look. During rapid eye movements, the world doesn't smear as it should when your eyeballs flick across a room several times a second because your brain briefly dampens the incoming changes and pastes together a steady scene, which means the continuous view you trust is assembled from moments that were momentarily hidden from you. Another tell is the flash lag effect. Watch a bright flash near a moving object, and you'll swear the moving thing is ahead of where it should be at the moment of the flash, as if your perception extrapolated motion to keep the world coherent. And that's exactly the idea. Your brain runs a tiny forecasting model that guesses where things will be by the time its slower machinery can finish processing, so the experience feels synchronized even though it's built on delay. Other illusions reveal a quieter magic called postdiction, where later information edits your earlier experience, as in the colorify phenomenon. Two dots blink in different positions with different colors, and you see a single dot glide between them, changing color mid-path at a point where nothing actually appeared. Your mind writes a smooth story after it receives the second blink, then hands you the story as if it were lived in real time, which means the future, by a whisker, helps decide how you remember the present. This editorial window, often a few dozen milliseconds for quick sounds and up to a couple hundred for complicated sights, lets your brain integrate multiple senses so that a voice and moving lips line up, tolerating small misalignments the way a musician delays a note for groove. And it's why you can stand in a windy street and still feel like you inhabit a single, unified now instead of a stack of slightly out-of-sync feeds. If you want a somatic demonstration, clap your hands sharply and notice how your eyes report the movement before your ears deliver the crisp slap. The sound is physically slower through air, yes, but your brain also holds and fuses the late arriving audio so that the clap still feels like one event, not two. Your nervous system is constantly solving a jigsaw puzzle where some pieces are missing, some arrive late, and some don't belong, yet somehow you see the picture. Even your attention manipulates time. In the attentional blink, noticing one quick target can temporarily blind you to another that appears about 0.2 of a second later, not because your eyes failed, but because your limited processing bandwidth was still packaging the first moment for conscious delivery, demonstrating that awareness is not a raw feed, but a scheduled broadcast. Micro-edits happen on your skin too. The cutaneous rabbit illusion taps your arm in a couple of spots, and your brain invents hops in between, distributing sensation across time and space, so the pattern makes sense, which shows that perception cares more about building a plausible story than reporting isolated facts. None of this means your experience is untrustworthy in any practical sense. Your world is stable enough for catching a ball, pouring tea, or merging into traffic, but it does mean your sense of immediacy is a brilliant compromise between speed and certainty. A layered process where neurons first guess, then check, then revise, delivering a final frame only when it's coherent enough to act on, and by then, the true external moment has already advanced. Intriguingly, this strategy isn't a bug, but a survival advantage. Organisms that waited for perfect certainty would be outpaced by those that could predict and move, so your brain treats perception like controlled hallucination anchored by incoming data, trimming and nudging the picture so your hand meets the doorknob instead of empty air. Notice how this reframes memory too. If the present is already a curated past, then memory is a second-order reconstruction of a reconstruction. And that's why eyewitness accounts diverge and why your own recollections bend around context, mood, and expectation. Yet this flexibility is power. It allows learning, adaptation, and resilience. The same way a sports camera buffers footage so it never misses the crucial play. And if you worry that this delay steals something essential, consider what you gain. A buttery smooth world in which motion is stable, objects persist, and sounds align with sights. A life where you can read a sentence without characters dissolving during each eye jump and enjoy music as a flowing line rather than a stutter of notes, all purchased for the small price of a blink of time you never notice. So the next time you catch a flicker, the streetlight that seems to flash just before you decide it did, the rolling spokes that reverse direction in a video, the sudden shock of a near miss that you process only after the danger is gone, remember that your experience of now is a masterwork of inference, a carefully backdated postcard from the world stating, "Wish you were here," arriving a breath late, yet somehow exactly when you need it. And in that gentle offset lies a comforting truth. Perception doesn't force you to keep up with the universe's raw speed. It invites you into a slightly delayed, elegantly composed version where you can understand, decide, and carry on. Time runs at different speeds on you. You don't live in a single river of time. You stand with your feet in one current and your head in another, and the two slip past at slightly different speeds, the quiet consequence of gravity, bending not only space, but also the tick of every clock, including the one you carry in your cells. So while it feels like all of you is aging together, the part of you higher up is creeping ahead by a sliver, measurably, reliably, and strangely comforting once you see what it means. Start with the simple picture. The closer a clock is to a massive body like Earth, the more gravity it feels, and the more slowly it runs. And clock here doesn't mean just the thing on your wall, but anything that marks regular change. An atom's heartbeat of light, a vibrating crystal, your own biological rhythms. Raise that clock a little higher. Ease it into a region where gravity is slightly weaker, and it will tick faster. So your head, by living a meter or so above your feet, ages a tiny bit quicker than your toes do, by only a few billionths of a second per year at that height difference. But the key is not the size, it's the principle. Time is not uniform wallpaper glued to the universe, it is elastic to place. This isn't a thought experiment that lives only in textbooks. Labs have watched it happen with exquisite tools, called optical lattice clocks, that trap thousands of atoms and read their light with such steadiness that raising one clock the height of a notebook makes it pull ahead, a sign so clear that scientists talk about chronometric geodesy, the craft of mapping Earth's gravity by comparing the tempo of time itself, as if hills and valleys in the planet's potential could be surveyed by listening to how fast two clocks sing. The world beyond the lab keeps reminding us that this is real. The satellites that guide your maps carry clocks that, left uncorrected, would drift tens of microseconds every day because they live higher and they move quickly. And it's the careful balance of these effects that lets your phone tell you where you are instead of placing you blocks away, a quiet partnership between physics and daily life. Now bring that understanding back to your body and imagine time as a soft gradient laid over you from shoes to scalp. Not enough to split a person, but enough to make you a stack of slightly different rates that your mind stitches into a single story, the same way it fuses the colors and shadows of a scene into one picture. If you lived your whole life in a mountain town, you'd gather a few extra microseconds over a lifetime compared to a twin at sea level, and that difference is too small to feel yet big enough to measure, which is the signature of deep truths in physics. They hide under the noise of daily experience but refuse to vanish when you look closely. You might wonder whether motion complicates the story, and it does in the most elegant way, because your head traces a slightly larger circle than your feet as Earth spins. It moves a touch faster, and moving clocks run slow, which nudges your head's time in the opposite direction. But near the surface, the effect from gravity dominates, so the overall result still favors your head. It's a reminder that nature rarely gives you just one lever. Several are always at work, and part of wisdom is learning which one matters more in a given setting. Notice how this reorients your idea of equality. If time runs differently from place to place, then fairness in physics doesn't mean the same for everyone, everywhere. It means the same laws applied with full attention to context, and that's oddly human. Our judgments, like time, depend on where we stand. There's another layer here that can change how you feel about living day to day. If time is slightly faster for the part of you that looks outward and a touch slower for the part of you anchored to the ground, then every breath quietly contains a lesson about perspective. When you lift your gaze, even by a little, you move into a roomier tempo. And while that doesn't transform hours into more hours, it suggests something gentle about outlook. Sometimes, the difference between feeling rushed and feeling spacious is a matter of position, of stepping into a lighter field, of remembering that not all pressure comes from clocks. And yet this is not a license to escape the ordinary. Rather, it invites you to savor it with new texture. The walk up a staircase, the view from an airplane window, the way your ears pop as pressure changes, each is a soft reminder that the world is layered, that up is not only a direction, but a shift in the pace of existence. You could even think of cities and mountains as tuning forks for time, shaping its local speed. When scientists first confirmed that clocks lower down tick slower, using beams of light climbing out of a lab's basement, they weren't just proving an equation. They were discovering that every address in the universe comes with a time signature, and yours does too. Your apartment, your street corner, the park where you sit to read. If this feels unsettling, let it also feel kind. You are not late to your own life. You are simply embedded in a world where simultaneous belongs to neighborhoods, not to all of space. And the miracle is that your body and your instruments have learned to navigate that patchwork with easy grace. The truth is, you've been living with these differences all along and thriving, and knowing about them can be a subtle antidote to the tyranny of the single ticking clock, the kind that insists there's only one pace for everything. Instead, you can hold a more generous image, time as terrain, varied and interesting, with gentle slopes even across your own height, and yourself as a traveler who already knows, deep down, how to walk those slopes without tripping. So when you lie down at night and your head rests closer to your feet, your personal gradient briefly softens, and when you rise in the morning, you return to your daily climb, gathering those extra nanoseconds like dew, invisible but real, proof that the universe pays attention to where you are and rewards you with a pace that matches your place. A small, enduring wonder, which, once seen, changes nothing about your routine, yet quietly reframes everything you thought the word now must mean. Empty space pushes and pulls. You expect nothing to do nothing, yet when two uncharged, mirror-smooth metal plates face each other a hair's breadth apart, they feel a real, measurable pull that seems to rise out of emptiness itself. And the first time you hear that, it sounds like folklore, until you see how it's tested and why it happens. The quantum fields that fill space are never perfectly still. Think of them not as sparks flying around, but as a restless background hum, and boundaries like metal plates change, which ripples can exist between them. Only certain wavelengths fit in the gap, while the boundless outside can host many more. So the pressure from the outside hum beats the pressure from the inside hum and nudges the plates together, a tiny force that grows dramatically as the distance shrinks. Hendrik Casimir worked this out in the late 1940s, while at a research lab that made light bulbs and radios, which is perfect, because this is radio quiet wizardry, no charge, no current, just geometry editing the vacuum. Decades later, experimenters caught it in the lab with delicate setups. A torsion pendulum feeling the twist from a sphere held a hair from a plate. An atomic force microscope sensing deflection as a gold-coated sphere crept within hundreds of nanometers of a gold surface. And trial by trial they learned to tame every mundane imposter. Residual electrostatic patches on real metals. Microscopic roughness. Tiny tilts so small you need lasers to notice them, until what remained tracked the prediction. Closer means stronger, with forces that for a 1 centimeter square area reach millinewtons when the gap is near 100 nanometers, and climb toward everyday pressures when the gap narrows to a few times the size of a molecule. The phrase "from nothing" is poetic but not quite right, and that's where the idea becomes honest and exciting. It isn't that emptiness creates a pull. It's that when you put boundaries in a fluctuating field, you change the energy stored in those fluctuations, and nature always answers such changes with a force. Push the plates apart, and you let more modes back in. Lower the energy inside, and the system resists. Move them closer, and you squeeze out options. Raise the energy, and the system tries to relax by pulling back. Zoom in further, and the story merges smoothly with forces you already half know by other names. At very small separations, the attraction looks like the retarded van der Waals force, arising from jittery clouds of charge that dance in step through the field. While at larger separations, the finite speed of light matters, and the interaction becomes what we call Casimir. Materials matter too. Real metals do not reflect perfectly. So the force softens compared with the ideal case, and warmth matters, because thermal ripples ride atop quantum ones and start to contribute when the gap is closer to the thickness of a red blood cell. Even the choice of environment matters in wonderfully practical ways. Immerse the plates in a carefully chosen fluid with the right optical properties and, counterintuitively, the force can flip sign and become repulsive, a laboratory trick that has been demonstrated with gold and silica surfaces in a specific liquid that tilts the balance of field fluctuations. Geometry is a sculptor as well. While parallel plates are the clean thought experiment, experimenters prefer sphere plate for alignment ease, and theorists have shown that corrugations, holes, and anisotropy can steer not only the strength but the direction, and even the torque. Two birefringent slabs prefer to twist toward a shared optical axis purely because of vacuum fluctuations. A tiny Casimir torque that has moved from prediction to measurement with ultra-sensitive setups. If you want the number sense more than the equations, here is a feeling for it. At a gap around 100 nanometers, the pressure is only a few dozen pascals, gentle, like the weight of a sheet of paper spread over a postcard. But shrinking the gap by a factor of 10 swells the pressure by orders of magnitude, and by the time you are near 10 nanometers, the push compares to atmospheric pressure, strong enough to matter for micro-machines. And that is where the effect quietly intrudes into engineering. In the realm of micro-electromechanical systems, where moving beams, switches, and mirrors operate at micrometer and nanometer gaps, Casimir attraction contributes to stiction, the tendency of parts to stick shut after they touch. While at the same time it can be repurposed as a resource, designers can harness the ever-present pull as a built-in spring or actuator. Once they understand how materials, patterns, and media tune it, the dynamic side of the story is equally mind-stretching without asking you to swallow myths. Change a boundary fast enough, say, by rapidly modulating the electrical length of a superconducting circuit that acts like a mirror, and you can coax real, detectable microwave photons out of vacuum fluctuations. The dynamical Casimir effect. Not because energy popped from nowhere, but because you fed energy into the boundary's motion, and the field took it in the only currency it trades. Quanta. You can see kinships everywhere once you know what to look for. Single atoms feel a version of this near surfaces, shifting their energy levels and feeling tiny tugs that alter their fall in an atom chip. An effect measured with ultra-cold gases and atomic beams. Nanostructured surfaces reshape the sea of modes like breakwaters in a harbor, making the local vacuum thicker or thinner for certain wavelengths. Graphene and other two-dimensional materials, with their unusual optical response, offer knobs to tune the interaction in ranges that ordinary metals do not, hinting at designer vacua with tailored forces. All of this teaches a quiet philosophical lesson that costs no poetry to state. Empty, in physics, rarely means nothing. It means no excitations you decided to count. And even that tidy definition can change when you change the stage. The safest way to hold it is to think of space as an instrument that resonates differently when you bring in walls, tips, slits, or fluids, and the Casimir force, as the hand on your shoulder, reminding you the instrument is still there when the music seems to stop. If someone tries to use this to sell you perpetual motion or free energy fantasies, you have a simple defense. Every measurement sits inside a careful energy bookkeeping that includes the boundaries, the drives, the heat, and the field, and every honest experiment balances its accounts. The real wonder needs no embellishment. Engineers must account for a force that did not even have a name a century ago. Metrologists can weigh it with devices sensitive enough to feel the whisper of a fingerprint. And you, standing in a seemingly quiet room, can know that even between two dust-free plates, in a vacuum pumped as clean as a starless night, the world refuses to be blank. It presses and relaxes, it leans and lets go, it hums invisibly, and if you give that hum the right shape, it will place a hand on matter and move it. A teaspoon that weighs a mountain. You think solid means stubbornly packed, but the universe has a stricter teacher. Take a teaspoon. Imagine scooping from a dead star's heart, and you'd lift something that on Earth would crush through bedrock like a meteor. The mass of a mountain condensed into a spoonful, not by magic but by ordinary matter forced into extraordinary closeness. A lesson in how far atoms can be pushed before they surrender their familiar structure. Begin with a massive star that burns bright and fast, fusing light elements into heavier ones until it reaches iron, the point where fusion no longer pays its energy bills. And when the core can't support the outer layers any longer, gravity wins in a single catastrophic lurch. The star's core implodes, and an outward blast, what we call a supernova, rips off the envelope while the center slams to a stop as a neutron-star, a sphere only about 20 kilometers wide yet holding more mass than our sun, with surface gravity so intense that if you could stand there your weight would multiply by about 100 billion. What used to be atoms are no longer the social units of matter. because the pressure is high enough to crush electrons into protons, forming neutrons and neutrinos, and you're left with nuclear matter. Neutrons packed shoulder to shoulder with a smattering of protons and a fog of electrons weaving through, a kind of gigantic atomic nucleus held together not by a shell of electrons, but by gravity, and by the strong force that lets neutrons huddle without flying apart. Step outward from the center and the density falls, and the star reveals a layered personality. Deep inside may be a uniform neutron-rich fluid that behaves like a superfluid, able to flow without friction, while the protons pair up into a superconducting state that carries currents with zero resistance. And then, approaching the crust, the balance of nuclear forces and pressure gets weirdly artistic, sculpting nuclear pasta phases where matter arranges into lasagna-like sheets, spaghetti-like strands, and gnocchi-like blobs because those shapes minimize energy under crushing conditions, before finally giving way to the outer crust, a grid of heavy nuclei locked in a crystal lattice with a sea of electrons, the stiffest solid known. This outer crust can carry enormous stresses with a shear strength that dwarfs anything on Earth, which means neutron stars can literally crack, starquakes that shift the crust by millimeters or less, but release energies that flicker across the galaxy, and we sometimes catch the signature as soft gamma-ray flares from magnetars. Neutron stars with magnetic fields so intense they would erase your credit cards from halfway to the moon. The numbers that sound like tall tales are grounded in measurement. We know these objects exist because we time the radio pulses from pulsars, neutron stars that sweep beams of radio light like lighthouses as they spin, and some spin hundreds of times per second with clock-like stability, then glitch suddenly, jumping a hair faster because superfluid neutrons in the interior unpin, transferring a whisper of angular momentum to the crust. A tiny mechanical hiccup telling you that inside this solid lies a quantum fluid. We've weighed them by watching the dance of binary systems, where two neutron stars tug each other, and the timing of their pulses betrays their masses, and in a few cases the numbers climb above 2 suns, ruling out some of the squishier ideas for the star's internal recipe, because anything too soft would collapse under that much weight. We've traced their silhouettes by measuring how their hotspots brighten and dim as they spin. The light bent by gravity so strongly that you can see more of the star's surface than you should be able to if space-time were flat. This light bending, combined with the way the pulses are shaped, gives a handle on the radius and therefore on how stiff the matter must be to hold that shape. And in 2017, the universe handed us a direct laboratory when 2 neutron stars collided and shook space-time hard enough for detectors to record the gravitational waves. Subtle ripples whose shape, rise, and fade were sensitive to how easily the stars deformed under each other's pull, once again narrowing the options for their internal physics. While telescopes watched the afterglow change color over days, a kilonova, because freshly made heavy elements like gold, platinum, and rare earths were spewing into space and decaying, proving that some of the jewelry on your hand was likely cooked in a sky-shaking neutron-star merger. Come back to density, because that's what reframes solid. The nucleus of an atom already packs almost all the mass into a tiny volume, but atoms themselves are mostly space-defined by electron orbits. In a neutron star, gravity erases that space, knocking the chairs close at the cosmic table. So 1 cubic centimeter, think of a sugar cube, can weigh 100 million tons or more, and a teaspoon of the inner layers would tip the scales on Earth at 1 billion tons. Figures that vary depending on exactly where in the star you scoop, but all of them humiliating for any earthly notion of hardness. Stand on the surface and drop a paperclip, and it would smack down at a significant fraction of light speed in a microsecond, liberating enough energy to vaporize miles of landscape. Not because paperclips are special, but because gravity is king when matter is that compact. Even the thin mountains on these stars are nothing like ours. A bump only a few millimeters tall can strain the crust to its limits, and such tiny asymmetries, held in place by the star's unheard-of shear strength, might broadcast continuous gravitational waves as the star spins, a whisper the next generation of detectors is trying to hear, because catching that tone would tell us how the crust yields and how magnetic fields braid the matter. Meanwhile, the star cools in a distinctly non-earthly way. Within minutes after birth, it dumps energy in a flood of neutrinos that sail through matter as if it weren't there, then spends tens of thousands of years glowing in X-rays as it settles. And the details of this cooling betray whether exotic ingredients lurk inside. Do particles called hyperons appear? Do neutrons pair up in a way that opens or closes certain cooling channels? Does some even stranger phase like quark matter show up at the core? We don't need to invoke fiction to make any of this dramatic, because the plain facts already rewrite our sense of solidity. Concrete seems reliable until you compare it with a lattice that can hold back 100 billion gravities. Steel seems unyielding until you learn that the neutron-star crust may have a breaking strain 10 billion times greater than rock. And hard becomes a provincial word once you've met a place where matter is literally a crowd of nucleons sharing elbows. And yet, for all this alien strength, these objects stay comprehensible through familiar ideas pushed to their limit. Pressure balancing pull, rigidity resisting shear, frictionless currents flowing through a conductor, heat escaping through radiation. Nothing about the list requires breaking the rules, only following them into regimes humans don't inhabit. Perhaps the most humbling piece is that your body, your desk, your city, everything you call solid is a gentle arrangement compared to this, held up mostly by the distances between atomic nuclei and by electrons politely refusing to share certain states. While a neutron star is the same recipe of protons, neutrons, and electrons, but crammed so tightly that structure gives way to crowd, and crowd becomes a fluid with the stiffness of a stone. So when you hear a teaspoon that weighs a mountain, you're not hearing a slogan. You're hearing a compressed story of stellar death, quantum pressure, nuclear architecture, and the stubbornness of matter under crushing gravity. And if that changes how a rock feels in your hand, good. Because the rock is a local custom called solid, and somewhere above a supernova remnant, a tiny sun cinder is spinning, cracking, and singing through space to remind you that even our most familiar words are flexible, and that reality has versions of hard we barely have language to hold. Your brain predicts reality first, sees it second. You don't wait for the world to arrive. You lean forward and meet it halfway, running a quiet rehearsal of what will happen next, and then checking reality against your draft. And most of the time that fast guess is so good, you don't notice you're guessing at all. What we call perception isn't a camera feed, but a negotiation between expectation and evidence. A layered conversation where deep brain regions send down their predictions about edges, voices, textures, meanings, while incoming signals push back with their corrections. And what you experience is the truce they sign every few milliseconds. A best fit story that is fast enough to act on and accurate enough to trust. You can feel this when you read quickly and your mind auto-completes a word before your eyes finish scanning it. Or when you walk through a dim hallway and somehow still see the furniture at the edges of vision. Your brain uses memories of rooms, the typical height of chairs, the way corridors are laid out, to sketch the scene, and only spends precious processing power on the parts that don't match the sketch. In speech, this is constant and life-saving. Noisy audio on a bad line becomes crisp because you predict missing consonants from context. A phenomenon so robust that if a burst of static replaces a letter, your mind will hear the intended sound anyway. A graceful fraud that keeps communication flowing. Even taste bends to expectation. Wine judged by label and price really does taste richer to most people because the brain's what this should be like signal sharpens and amplifies the incoming flavor. And scanners show reward areas rising to meet the story, which is why placebo works not as a trick, but as a biological pledge. Predict pain relief, and the body, primed by that belief, releases its own pain-dampening chemistry. Predictions shape touch and movement too. You can't tickle yourself because your motor system sends a copy of the outgoing command to sensory areas, telling them what to expect. So the touch that lands matches the forecast and gets discounted. And out of this same forecast and subtract method, your ability to move with grace is forged. The cerebellum is full of circuits that anticipate the consequences of your actions and correct them in flight, which is how you can catch a falling glass or thread a needle without calculating trajectories or angles. Look at athletes timing a pitch or a pass. The ball is not simply tracked, it is predicted, its path extrapolated a little ahead of where the eyes currently see it. So the hand arrives in time for a moment that has not fully happened yet. High-level meaning, not just raw sensation, gets the predictive treatment. When you enter a conversation, your brain points its spotlight where it expects relevance to appear, which is why a single word you care about cuts sharply through background noise at a party, and why misheard lyrics snap into clarity once you read them. The line you expect reshapes the sounds you receive. Illusions are not failures, but windows into the rules of this prediction game. In the hollow mask illusion, a concave face flipped toward you looks convex because your brain's prior knowledge that faces bulge outward is so strong that it overrides the geometry. And in the classic checker shadow trick, squares shaded by a shadow look lighter than identical squares in bright areas because your visual system assumes light sources and compensates for them, focusing on surface color rather than raw brightness. On a deeper level, this same architecture applies to your body map, the felt sense of ownership over hands and heartbeat. In the rubber hand illusion, synchronous taps on a fake hand and your hidden real hand make your brain's prediction, that hand I see being touched must be mine, win over the signals from your skin, sliding ownership toward the rubber. And with practice, you can even learn to nudge your heartbeat with nothing but expectation and attention, showing that interoception, the brain's model of internal organs, is also a prediction tuned by feedback. None of this means your senses are flimsy, it means the brain is efficient. Raw data are noisy and slow, while a well-trained forecast is fast and usually right. So the system gives predictions the first word and lets actual input speak up when it disagrees. And what we experience as surprise is the audible protest of the world saying update your model. Learning then is the art of adjusting those models. A child's first encounters are full of error signals because the world keeps saying not quite. And over time those errors sculpt more refined expectations that dogs have faces and fur and a certain smell, that gravity makes mugs fall unless something holds them, that certain expressions predict anger and others laughter. And this is why encountering a culture with different habits or foods can feel like a storm of tiny surprises. Your priors need tuning. When the balance between prediction and evidence tilts too far, experience can skew. If the brain leans heavily on prior beliefs, ambiguous shadows become threatening figures, random creaks become voices, and hallucinations can be understood as the mind's models speaking too loudly over muted data. If the brain weights incoming signals too strongly and struggles to rely on prior context, the world can feel painfully vivid and unpredictable, each change demanding attention, a state some researchers associate with certain forms of sensory sensitivity. Anxiety fits the framework too. If the model overestimates danger, prediction errors multiply because ordinary noises don't match a threat-filled forecast, and the system spirals into scanning and confirmation, a feedback loop that feels like dread. Yet the same mechanics can heal. Therapies that change how you interpret bodily signals, reframing a racing heart as excitement instead of catastrophe, adjust the prediction and quiet the mismatch. And exposure therapy works by letting the brain discover that expected harm doesn't follow, gently ratcheting priors towards safety. The predictive brain also explains why habits are powerful. Rehearsed sequences, tying shoes, driving a familiar route, become strong expectations of what comes next, freeing attention to handle interruptions. And it explains creative leaps. Artists and scientists generate unusual combinations by relaxing strict priors and entertaining patterns that don't normally co-occur, then testing them against the world. Technology borrows the same playbook. Noise-cancelling headphones forecast the next wiggle of unwanted sound and play an opposite wave just in time to flatten it. And modern keyboards know which letters you meant by predicting words from the ones you've started, correcting typos before you even notice. Step back and notice the ethic hidden in this biology. You are not passively imprinted by reality. You are in a constant dialogue with it, proposing and revising. And that means agency. Your expectations are not fixed, they can be trained. And because they steer what you perceive and how you feel, Training them is a practical tool. You can practice listening for counter-evidence instead of confirmation. You can label a sensation as information rather than alarm. You can design environments that feed better data, a tidy desk, gentler lighting, consistent routines, so your forecasts grow calmer and more accurate. Even wonder becomes a skill here. To cultivate curiosity is to loosen your grip on a rigid model, just enough that surprise becomes a teacher instead of a threat, letting the world correct you without bruising your pride. And when you end a day, consider how many predictions worked so well you forgot they were guesses, voices understood on a busy street, steps taken without measuring distance, faces recognized from a glance, meanings inferred from half a sentence. And feel how remarkable it is that the mind you carry can run a universe of tiny experiments every second, updating itself in the background while you get on with the business of living. The gift of knowing this is not cynicism, but tenderness. If your brain sometimes gets it wrong, it's not because you're broken, it's because you're bold enough to go first, to paint a provisional world and then let reality lean in and finish the picture. And in that partnership between forecast and fact lies a durable kind of intelligence, the kind that helps you walk through uncertainty with eyes open, willing to be corrected, and strong enough to change your mind. Bananas glow. You don't have to visit a reactor to meet radioactivity. You can meet it in a fruit bowl and in your own skin, because bananas carry a faint signature of the cosmos, and your body whispers light so softly that you need a dark room and exquisitely sensitive detectors to catch it. And once you learn why, glow stops sounding like science fiction and starts sounding like a quiet property of living and ordinary things. Begin with the banana, because it is the friendliest doorway into the idea. All potassium in nature includes a tiny sprinkle of a rare isotope that occasionally decays, and bananas are rich in potassium for healthy nerves and muscles. So a banana carries a trace of this isotope and emits a faint gamma ray now and then, far below anything you could see or feel, but real enough that a port scanner that looks for smuggled materials may raise an eyebrow at a shipping container of bananas for a moment. This is where the playful notion of the banana equivalent dose came from, a way scientists joke about perspective by saying a banana works out to about 1/10 of a microsievert, which is tiny compared with what you absorb from the ground beneath you, the air you breathe and the sky above you over a year, and yet the banana's nudge is honest and measurable with the right instruments. The lesson isn't that fruit is dangerous. The lesson is that radioactive and natural are not opposites, because the world is built from stable things with a gentle seasoning of unstable ones. And those slow, steady changes are part of the background you have lived in since birth. Your body carries the same flex of the universe's long story. You contain potassium and a little carbon that occasionally steps down to a lighter form. So inside you, every second, thousands of tiny changes occur, each too small to matter alone, but together forming the quiet hum of natural radioactivity that passes for normal life. Which is why hospitals and labs need special shielding and careful counts to tell the difference between you and the samples they study. The second half of the glow story is not about particles from within, but about light from chemistry. The ultra-weak emissions called biophotons that most living tissues produce during ordinary metabolism, often in the visible range, but so faint that your eyes can never see them. Think single to hundreds of photons per square centimeter in a second, and yet sensitive cameras and photomultipliers can, if you shut out every stray glimmer and wait. The source is not magic, but chemistry with a dramatic side. When cells deal with oxygen, they sometimes form reactive byproducts that briefly leave molecules in excited states. And when these states relax, they can release a photon. And because life runs on countless such reactions at once, a drizzle of light is always being written into the dark, its pattern reflecting the cell's current balance between activity and cleanup. Researchers have photographed this light from leaves adjusting to stress, from fish eggs as they develop, from human hands as they rest, and even from faces over the day, hinting at a circadian rhythm in our faint self-luminescence, brightest in the late afternoon when metabolism is most busy, and dimmest in the small hours when things are quieter. If you want a home analogy that separates myth from reality, remember this. The old watch dials that glowed by themselves did it because paint makers mixed a strong source with a phosphor, so the constant radiation kept the phosphor excited, while the soft light from a person or a plant is not a self-charging lamp, but the sum of countless tiny reactions that occasionally end in a photon, so weak and spread out that you need darkness and patience to collect them. The banana story has its own popular myth to clear up. A banana does not light up a room, it does not cast a green halo, and it does not make your countertop dangerous. Its glow is a statistical fact that trained electronics can count, not a visual glow you could film with your phone in the dark. The beauty of this is that it teaches dose sense better than any lecture. The average person receives a few millisieverts a year from nature, mostly from a gas that can seep from rock into basements and from cosmic rays that shower down from space, with your location and habits nudging the total up or down. And a single banana sits so far below these numbers that you would need to eat stacks every day for years to move the needle. And even then, the potassium level in your blood is what your body tightly regulates, not the radioactivity per se, which is why medical advice about diet focuses on balance, not on counting fruit as if it were a hazardous source. Everyday objects extend the lesson in perspective. Granite countertops contain trace elements that occasionally decay. Cat litter made from certain clays can set off a detector designed for scrap metal screening, and a bag of salt substitute that uses potassium chloride carries more natural activity than ordinary table salt because it contains more potassium. While Brazil nuts sometimes test higher than other foods because their deep roots gather minerals from soils rich in certain isotopes. But in each case, the scale is tiny, and the right response is not fear but respect. The world is a tapestry of small signals, and understanding the weave gives you control. Once you appreciate biophotons, a new set of possibilities opens that has nothing to do with scare stories and everything to do with care. Because this ultra-weak light reflects oxidative stress and repair, scientists are exploring whether its patterns can non-invasively report on skin health, the freshness of stored food, or how well plants are coping in drought or disease. Almost like listening to a whispering stethoscope placed on metabolism. Experiments show that when tissues are injured or stressed, the trickle of photons rises, and as repair processes dominate, it falls. And in some cases you can see afterglow that follows an intense light exposure. A delayed luminescence tied to how molecules store and release energy, giving another window into how a living surface is doing. This is not a substitute for medical imaging or blood tests, but it is a promising lens for research and maybe for future diagnostics that watch health without touching it. You can carry the idea further into the invisible world around you. A pile of ripe bananas in a warehouse, with their slight emission, can occasionally nudge sensitive port monitors the same way ceramic tiles or fertilizers can. And the practical people who operate these scanners learn to read the signature like a dialect. Different materials have different fingerprints, and the sharp peaks from something risky look nothing like the soft, natural murmur of produce or clay. This kind of literacy matters because it prevents overreaction and keeps attention for the signals that truly require it. In the realm of education, the banana has become a favorite prop because it lets teachers talk about isotopes without equations, about the difference between scary words and real risks, and about the unity between you and the things you eat. You and the fruit share a light brush of ancient stardust that still rearranges itself from time to time, and you both share chemistry that occasionally sighs out a photon. If the thought of natural radioactivity ever makes you uneasy, there is a balancing truth that belongs beside it. Life on Earth has unfolded under this steady background for billions of years, evolving repair systems and checkpoints that are good at handling the everyday trickle of damage. And what matters most to health are the big levers you already know. Sunlight without burns, air without smoke, water that is clean, food that is varied, while the banana on your plate is a symbol not of harm, but of how deeply you are connected to the real fabric of nature. And if you want a small practice to anchor the lesson, the next time you peel a banana, let the simple facts sit in your mind. This sweetness grew from minerals gathered by roots and sunlight bottled by leaves. It carries a whisper of an isotope that is older than Earth, and so rare you can only detect it with careful instruments. And when you set the peel down and turn off the kitchen lights, your own skin will continue to emit an undetectable shimmer born of metabolism's sparks. Not enough to see, but enough to measure with the right ears, which is perhaps the most practical definition of wonder. Finding out that ordinary things are singing so softly that only curiosity lets you hear them. The closing comfort is this: between the banana's faint signature and your body's gentle glow, you can feel the difference between the loud stories that frighten and the quiet truths that teach. And once you learn to hear the latter, the world becomes less alarming and more alive. A place where even a piece of fruit and the back of your hand carry a trace of the universe's ongoing conversation in the smallest possible voice. Magnets can levitate things quietly. You don't need roaring engines or hidden strings to make an object float. You can make it hover in a room so quietly that the loudest thing is your own breath. And the secret is not a trick magnet, but a special kind of matter chilled until it slips into a phase where electricity flows without resistance, and magnetic fields behave like well-trained waves. Start with the simple miracle. A superconductor set above a magnet will levitate, not because like repels like, but because when this material gets cold enough, it refuses to let magnetic fields pass through its interior, pushing them out and generating currents on its surface that exactly cancel the field inside. Which means the magnet and the superconductor dance in a balance that lifts the superconductor into the air. That basic levitation is already startling. Yet the truly eerie version, the one that looks like an invisible rail system, is called quantum locking, and it comes from a class of superconductors that, instead of completely expelling a magnetic field, let it thread through in tiny, countable tubes wherever imperfections or grain boundaries offer a path, and then they clamp those threads in place. Each tube is a microscopic tornado of supercurrent, carrying a single, universal packet of magnetic flux. And when many of these vortices pin themselves in defects throughout the material, the superconductor is not free to slide wherever it wants. The magnetic field lines are literally anchored inside it. So the object can hover at a fixed height, angle, and position relative to the magnet, as if welded to an invisible track. You can see this in live demonstrations using a coin-sized disc made of a ceramic compound often called YBCO, cooled in a bath of liquid nitrogen until it crosses its transition temperature and turns superconducting, then placed near a magnetic track that has alternating poles laid out like a tiny roller coaster. Tilt the track, flip it upside down, even turn it vertical, and the disc just hangs there at the same gap, gliding forward with a fingertip push, stopping when you stop, holding itself locked in place, because the field lines that penetrated it while it cooled are now stitched through its body. The first time you witness it, your brain searches for hidden hooks, but there aren't any. The restraint is inside the material itself, a form of stiffness that comes from the way the superconducting state organizes motion, so that any attempt to move off the rails would require the field lines to slip through, and that slippage is resisted by the defects pinning them. This quiet rigidity is what differentiates quantum locking from a simpler cousin. Plain magnetic levitation based on eddy currents or on strong repellents tends to be wobbly and needs constant stabilization, while a pinned superconductor levitates in a way that feels like a magnetic version of a ball bearing pressed into a groove. There's almost no friction along the path, yet there's strong resistance to motion across it. If this smells like sorcery, it helps to remember that all magnets and metals have personalities in magnetic fields. Ordinary conductors can briefly oppose changing fields by swirling currents that cost energy. Some materials are weakly repelled and can float over outrageously strong magnets. Thin pyrolytic graphite will do this over a checkerboard of poles, but that effect is fragile and small. Superconductors take repulsion to its logical extreme, with perfect lossless screening currents, and Type II superconductors go one better by allowing certain threads of field inside without destroying the state, creating the perfect invisible rail and clamp combination. The quantum label is not marketing. Those flux tubes carry magnetic field in discrete chunks set by fundamental constants of nature, and their behavior, including how they pin, how they arrange in lattices, and how they creep under force, is governed by quantum rules scaled up to something you can move with your hand. The calm glide you see is powered by wholly practical choices. Ceramics like YBCO belong to the family called high-temperature superconductors, which switch on their strange phase around the boiling point of liquid nitrogen, a cheap, classroom-friendly coolant that lets you pour fog over the disk and make it float in minutes. If you warmed that disk up, the effect would vanish in a quench, because superconductivity has hard limits: a critical temperature, a maximum magnetic field strength, and a maximum current density, any of which, if exceeded, breaks the delicate order and restores ordinary resistance. The price of the magic is staying inside the window where the rules hold. Materials scientists work hard to widen that window by engineering pinning centers, tiny defects, nanoparticles and columnar tracks etched by ion beams that grab those flux vortices more firmly, because pinning that is too weak lets the vortices drift and dissipate energy, ruining the lossless character under heavy loads. This isn't just for show. Applications try to harness the stability and near-zero friction in precision bearings that can suspend a rotor without lubricant, in energy storage flywheels that spin for hours with minimal loss, and in magnetic shielding and positioning systems where "stay exactly here" means across micrometers for weeks. You might wonder about the iconic high-speed trains. Many maglev systems don't rely on superconductors at all, but on carefully arranged permanent magnets and active control that stabilizes the gap, trading cryogenics for complexity. Still, prototypes and some research testbeds use superconductors because quantum locking offers passive stability. You can park a heavy platform over a track, and it will center itself without feedback electronics, a property that gets traction in concepts for cargo movers, vibration-free stages for microscopes, or even launch assist rails. None of this requires wishing away compromises. High-temperature superconductors are brittle ceramics, hard to make in long, flawless pieces. Cooling adds cost and bulk, and geometry matters, since the locking only works relative to the field lines present during cooldown. Change the field too much, and you must re-cool to reset the stitched pattern. Yet even in these practical wrinkles, there is elegance, because the technology mirrors the underlying physics. Pinning centers need to be tailored, like the grooves in a well-made key, and the feel of a levitating puck, the way it glides along, the way it resists lifting off the rail, is a fingertip translation of abstract ideas like screening currents and vortex lattices. If you want to separate hype from truth, keep two images. First, a superconductor above a magnet with a steady, quiet gap, held in place by the field lines that penetrate and pin. This is quantum locking. Second, a simple diamagnetic levitation that wobbles and falls if you sneeze. This is not. Both are real, both are beautiful, but only one gives you that uncanny, bolted to the air stability. And if you need a practical scale to trust, remember that classroom tracks a few tens of centimeters long can carry a disc with a metal block atop it without sagging, while research setups scale to heavier loads with careful design, and the force can be tuned by changing the magnet pattern and the number and strength of pinning sites in the superconductor. There is a human lesson tucked inside the physics. When you see the puck slide around a curve, upside down, then stop in midair as if a hand steadied it, you are watching a compromise made perfect. Freedom along one direction married to commitment in another. And life often rewards the same posture. The ability to move with almost no friction toward what matters, while being firmly anchored against the pulls that would tip you off your path. In a world noisy with claims, this is a quiet wonder that does not need exaggeration. Chill a ceramic until it forgets resistance. Invite a magnetic field to draw clean lines through it, and the object will find rails you cannot see. Glide where you guide it and hold fast where it must. A floating signature written by quantum rules big enough to touch. Light can slow and stop. You're told nothing moves faster than light. But here's a softer, stranger truth. Under the right conditions, you can persuade light to tiptoe, to crawl, and even to hand you its pattern so you can hold it still in matter and give it back later, like saving a file and reopening it. by teaching a cloud of atoms to act as both librarian and shelf, a trick called electromagnetically induced transparency that turns an opaque medium clear and carves an ultra-narrow window where light can slip through at a pace you choose. The stage is simple to picture even if the choreography is subtle. Take a vapor of alkali atoms. Rubidium is a favorite, whose electrons prefer certain energy steps, and shine two carefully tuned beams through it, a strong control beam that prepares the atoms and a faint signal pulse whose fate you care about, and watch something counterintuitive happen as the control beam reshapes the atom's options. Without preparation, the signal's color would be absorbed. Those atoms love to take that bite of light, but the control beam couples a second route for the electrons so that the two possible absorption paths interfere and cancel, not chaotically, but cleanly, opening a narrow transparency notch right where it used to be darkest. And the real magic is not just that the medium becomes see-through, but that near this notch, the refractive index changes very sharply with color, which means the signal's wave crests still ripple fast. But the pulse envelope, the part that carries information, slows dramatically, sometimes by many orders of magnitude. This does not break any cosmic law because you're not pushing energy or information faster than light. You're sculpting how a pulse is reassembled as it steps through the crowd of atoms, trading raw speed for an exquisitely steep form of dispersion that squeezes the pulse in space as it enters the medium. A microsecond pulse that once filled hundreds of meters of air can be compressed to millimeters inside the vapor, with its energy and patterns spread between light and the atom's collective state. Here's where slow becomes stop. If, as the shortened pulse nestles inside the medium, you gently dim the control beam to 0, the pulse doesn't vanish into heat the way ordinary absorption would devour it. Instead, its shape and even its phase are mapped into a long-lived coherence between two ground states of the atoms, a kind of whispering alignment of spins that stores the pattern without light actually traveling. And if you later turn the control beam back on, the atoms cooperate to rebuild the same pulse and release it, like reshelving a book back into the aisle. In the language researchers use, the traveling thing is a dark state polariton, a hybrid of a photon and a spin wave whose identity slides smoothly from mostly light to mostly matter, a slider you can move with nothing more than the brightness of a beam. And that adjustable blend is why this works both with classical flashes and with very weak pulses down to single photon wave packets, preserving delicate quantum properties like timing and phase. So the memory can serve in quantum networks instead of just classroom demos. The first time people coaxed light to crawl, they did it in an ultra-cold gas where thermal motion could not smear the stored pattern, and measured speeds that you and I can outrun. Walking pace for light in a lab should feel illegal, but isn't. And soon after, teams showed you didn't need costly cold, only the right buffering, magnetic quiet, and steady lasers in a warm cell to slow pulses by factors of 1,000,000 and then halt them for microseconds to milliseconds. Long enough to be meaningful for communications between quantum devices. It's not the same as freezing a beam in mid-air like a science fiction freeze ray. The outside world still follows its own clocks, but inside the prepared medium you have a moving window that can be opened and closed on demand. A place where the identity of a pulse can rest as an atomic pattern that drifts and decays only as fast as your environment scrambles it. That scrambling, called decoherence, sets the practical limits and gives the technique its earthy engineering flavor. Stray magnetic fields tug the two ground states apart and erode the stored alignment. Thermal motion in a warm vapor blurs the spin wave as atoms wander. Collisions twist phases out of sync, and imperfect lasers draw little scribbles on what should be clean lines. So experimenters fight back with shields of mu metal to hush ambient fields, with buffer gases to keep atoms from diffusing too far too fast, with carefully chosen polarizations and glass cells coated on the inside so atoms bounce without forgetting, with narrow line width lasers that don't jitter, and with timing sequences that gate, store, and retrieve with metronome discipline. Because the transparency window is extremely narrow, there's an unavoidable trade-off between how fast a pulse can change and how faithfully it fits through the slot. If your signal has a broad spectrum of colors, most of it won't match the window and will be lost. So successful storage often means shaping the pulse beforehand and matching it to the medium's bandwidth, like trimming a key to slide into a particular lock. The reward for getting all of this right isn't just a cool party trick. EIT memories can synchronize the arrival of single photons that originate far apart, a crucial ingredient for building quantum repeaters that will someday knit city-scale or continent-scale quantum networks. And they can buffer photonic qubits so that detectors and processors with different speeds can speak without missing each other. Even images can be stored. By making the control beam large and uniform, researchers have imprinted faint two-dimensional patterns into a vapor, letters, edges, simple pictures, and then retrieved them seconds later with surprisingly crisp fidelity, proving that this is not only a trick for one-dimensional waveforms, but a playground for spatial information as well. The same principles translate into solids with special impurities where long-lived spin states can hold patterns for minutes under cryogenic care, and into crystals where rare earth ions create clean shelves for photons to rest upon, suggesting hybrid platforms where fiber-carried light talks to an on-chip memory and back again. You might wonder how stopped light squares with your intuition that stopping a moving thing means removing its energy. And that's the subtlety worth savoring. What you stop is not a bullet, but a choreography. The relational pattern between a field and a medium. And when you press pause, you convert a traveling dance into a stationary one, storing not a photon in a jar, but the information that defined that photon's shape and timing, which is exactly what communication systems and quantum experiments need. There are siblings to this method, echo-based memories that use gradients like a photographic darkroom for light, or schemes that sculpt absorption profiles into combs, sew different slices of a pulse rephase together later. And each has its own gift of bandwidth, efficiency, and lifetime. But EIT's special grace is its everyday transparency. By turning darkness into a tunable window, it makes the medium itself your knob for speed and storage. And that tunability is why you can watch a pulse creep across a cell like a slow tide and then, with a twist of light, vanish into atoms and return on cue. The everyday lesson is almost domestic in its simplicity. Sometimes you don't need to build a box to keep a thing safe. You only need to convince the room to hold it for you, to make the room hospitable and quiet, and then to ask for it back when you're ready. So if anyone tells you light is always in a hurry, you can smile and picture a modest glass cell on a lab bench filled with a gentle vapor, a bright control beam humming through, and a tiny signal pulse entering like a traveler who has finally come home. Slowing, settling, laying down its story in the language of atoms, and later, on command, getting up again, intact and unhurried, ready to finish its journey. Objects can tunnel through walls. You're told walls keep things in and out, but in the quantum world, a wall is more like a misty hill, thick enough to block a bowling ball, thin enough that an electron's spread-out nature can smuggle a tiny fraction of itself to the other side. And once you grasp that, a surprising unity appears between the glow of the sun and the chips in your pocket. Both rely on tunneling, the rule that small things don't have to climb every barrier. They can sometimes slip through it. Begin with the picture you can hold in your head without equations. A particle isn't a hard dot. It's a wave of possibilities that fades with distance, and when that fading wave meets a barrier, it's not abruptly zero inside. It leaks a little, and if the barrier is thin enough or the particle light enough, a portion of the wave makes it to the far side and reappears there as a real arrival, rare but real. This is not hand-waving poetry. It leaves fingerprints you can measure. Heavy nuclei sometimes spit out helium fragments in a process called alpha decay, even though those fragments don't have the energy to climb over the nuclear wall. And yet the decay rates line up with the probability you'd expect if the fragments tunneled through. The sun, too, ought to be far dimmer if protons had to bang together with enough oomph to merge by brute force. But at the star's core, the temperature is only in the millions, not the billions you'd guess for a classical barrier. And fusion still happens because proton wave functions overlap and occasionally tunnel into a shared state, long enough for the strong force to lock them, which means every sunlit morning owes a debt to a quantum shortcut. Now zoom to a bench where engineers play with tunneling on purpose. A razor-thin insulator sandwiched between conductors becomes a gate that normally blocks electrons, yet lets a calculable trickle tunnel across. And from this simple element you can build devices that do things ordinary diodes and transistors cannot. Long before the modern microchip, a clever component called the tunnel diode showed negative resistance. Push a little harder and less current flows, because electrons resonantly tunnel through a narrow barrier at specific energies, a quirk that made tiny, fast oscillators possible. Today, the same principle is sharpened and repurposed almost everywhere. Your life touches electronics. The scanning tunneling microscope, a kind of fingertip made of electrons, brings an atomically sharp tip within a hair of a surface and watches the tunneling current change exponentially as the gap widens or narrows by angstroms, which lets you feel the positions of individual atoms and even nudge them around to spell letters or build tiny circuits. An everyday lab device that quite literally draws with probability. In memory technology, your phone's flash cells are programmed and erased by coaxing electrons to tunnel into and out of a floating island inside each transistor, where they sit for years, shifting the threshold that decides whether the cell reads as a 1 or a 0. And when manufacturers tightened dimensions too far, unintended tunneling, leakage, began to nibble battery life and data retention. A polite reminder that probability never sleeps. On the horizon of low-power computing, engineers are chasing tunnel field effect transistors, which use tunneling as the on-off gate so that current can switch sharply at lower voltages, promising cooler chips if materials and fabrication can tame variability. Even magnetic memory leans on tunneling in a different costume. In magnetic tunnel junctions, a nanometer-scale oxide slices between two magnetic layers, and the likelihood that electrons tunnel depends on whether those layers' north-south directions align. So the resistance itself becomes a memory of direction, the basis of a growing class of fast, durable memories. If you love superconductors, tunneling gives you another jewel without repeating old tricks. Put two superconductors across a slender barrier, and a supercurrent flows with no voltage at all, steered by the quantum phase on either side. The junction's response to microwave light is so precise that national labs use it to define standards of voltage and frequency, while sensitive versions, looped into rings, can detect magnetic fields so faint they register the whisper of distant brain activity. The ordinary world shows tunneling in more familiar clothing. 2. Sharpened metal needles in electron microscopes emit electrons into vacuum when high fields tug on their wave functions, letting you image surfaces at stunning resolutions. And rugged emitters built from carbon nanotubes promise the first prototypes of cold cathode displays. Chemistry has its own quiet tunnels. In frigid conditions where classical rates would plummet, light particles, especially hydrogen, can tunnel between positions along a reaction path, and some enzymes seem tuned to leverage this, shaving energy budgets and speeding steps that life depends on. Step back and notice how the same rule governs wildly different scales. In the nucleus, tunneling sets lifetimes measured in ages of rock. In stars, it balances the energy books of galaxies. In your laptop, it stores your photos and, when overdone, drains your battery. The connecting thread is not mysticism, but geometry and scale. Thin barriers, small masses, short distances, conditions that turn impossible into unlikely but frequent enough to matter. Because it deals in chances, tunneling invites a certain wisdom when you design or interpret systems. Device engineers work like gardeners, adjusting barrier thickness and height by choosing materials and layering them with atomic control, then measuring currents across spans of a few atoms to decide if the harvest is what they wanted. Physicists read tunneling signatures, the way current depends on distance, the way decay rates spike with small energy differences, as a language that translates structure into behavior. Even safety experts learn to hear it. The delicate leak currents in medical sensors can be signal or noise depending on context, so rather than shouting tunneling down, they shape it into the pathway they need. If anyone tries to smuggle woo into the story, you can guard the edges with simple sense. Tunneling does not allow messages faster than light. It does not make macroscopic objects pop through walls on command. and it never creates energy from nowhere. Every device and reaction balances its books, and the through-the-wall shortcut comes with a probability toll you can't evade. What tunneling does give you is subtler, and in a way, more generous. A reminder that nature's rules are flexible at small scales, that barriers are not absolutes but invitations to think in gradients, and that some of the most powerful tools we wield, the nanometer-thick switch under a camera pixel, the memory cell under a photo of someone you love, the starlight waiting on your windowsill, are born from events that each look vanishingly unlikely yet, summed over vast numbers, become the dependable background of modern life. And there is a quiet comfort in that. If the universe allows tiny chances to accumulate into steady realities, you are living in a world where persistence matters, where countless small acts can add up to light, warmth, and memory, and where even a wall can be less of a commandment and more of a suggestion, provided you are small enough, patient enough, and willing to let probability do its slow, beautiful work. Observation can freeze motion. You can stop a quantum system from changing just by checking on it too often. A result so counterintuitive, it feels like a proverb turned literal. The watched pot really does refuse to boil if you're watching is the right kind of physical interrogation. And this isn't a metaphor about attention, but a concrete rule about how measurement feeds back into the evolution of tiny systems, resetting their progress so frequently that transitions never get a chance to take hold. Begin with the simplest scene you can picture without equations. An atom is prepared to flip from one well-defined state to another under a gentle nudge, say, a resonant field that would normally make it cycle back and forth. And if you leave it alone, it executes that motion cleanly. But if you interrupt at very short intervals with a measurement that asks, "Are you still in the starting state?" each answer of yes collapses the atom's wavering superposition back onto the start, erasing the partial progress and forcing the system to begin the move again from zero. Done rarely, those checks barely matter, but done rapidly enough, they carve time into such fine slices that the system keeps resetting before the transition probability can grow beyond a whisper, and the net effect is a freeze. Motion that should have unfolded is stalled by the act of verifying it hasn't happened yet. This is not a philosophical trick. It shows up in the lab with clocks and counters attached. In a landmark experiment with trapped ions, physicists drove a transition that would make the ions hop between two internal levels, then peppered the evolution with probe pulses that asked which level the ions occupied. And as the interval between probes shrank, the expected Rabi flopping was suppressed, matching the prediction that repeated projective measurements interrupt the buildup of change. Similar logic has been pushed into platforms as different as ultra-cold atoms in optical lattices, where monitoring whether atoms occupy particular sites can halt tunneling between wells, and superconducting qubits on chips, where continuous weak measurements, less violent but steady, can catch and reverse quantum jumps in mid-flight, turning what used to look like sudden, untrackable events into guided, almost classical, trajectories that you can nudge with feedback to keep the system pinned. To avoid mystifying this, it helps to be precise about what measurement means. Not a human glance or a camera exposure, but any physical interaction that entangles the system with something capable of recording information about it. A probe pulse, a fluorescence check, an electrical readout. And once that record exists, even if no one ever reads it, the system behaves as if the alternatives it might have explored have been pruned away. So checking, still here, acts like a periodic pruning that prevents the branches from spreading. There's a deep timing reason for why this works that hides in the earliest moments of any transition. Right after a change begins, the chance of having changed grows not linearly but quadratically with time, which means at very short times the growth is feeble. And if you keep resetting the clock to zero before that gentle curve can bend into a faster rise, you hold the system in a perpetual prelude where nothing much accumulates. Stretch your imagination from two-level flips to processes like decay, and you find equally striking consequences. A photon trying to leak out of a cavity, an excited atom about to emit, or even a collective spin state headed toward dephasing, can be stabilized by measurement schemes that keep asking the right question at the right rhythm, a technique that blends naturally into quantum control where the goal is not just to observe, but to guard a fragile state against noise by projecting it back into a safe subspace again and again. Engineers call these Quantum Zeno subspaces, and they use either frequent projective checks or strong continuous coupling to an ancillary system that effectively monitors an error channel, making any move into the bad space immediately noticed and therefore suppressed, a strategy that complements error correction codes by reducing the rate at which errors happen in the first place. All this talk about freezing invites a caution that makes the subject more interesting, not less. If you set the cadence badly, probing not ultra-frequently, but on a timescale that resonates with the environment's own memory, you can get the opposite, the so-called anti-Zeno effect, in which measured systems change faster because each interrogation nudges them along rather than resets them. A reminder that in quantum mechanics, watching is an intervention with a sign and a magnitude, not a neutral act. Optics experiments show both sides of this coin. In nonlinear crystals or in waveguides, inserting absorbers or couplers that selectively ask about a particular path can either choke off interactions or stimulate them, enabling photonic switches where a gentle control beam decides whether another process proceeds, a practical device-level echo of the basic principle. A related but distinct family of demonstrations keeps the spirit while changing the setting. In one set, researchers let a many-body system expand from a small region and then apply local measurements that keep asking whether a particular site is empty or full. The result is a dynamical blockade that reshapes the pattern of spreading, effectively sculpting the pathway of quantum transport by painting regions as observed, and the shape you get depends on how strongly and how often you paint. In another, atoms trapped on a chip are encouraged to tunnel, but the act of imaging them with a very weak, frequent probe stalls their motion, a photographic version of "don't move" that relies on the same short-time reset logic. You might ask whether the Zeno effect is just dephasing in disguise, mere noise smearing the coherent motion until it looks flat, and careful experiments answer no. True Zeno freezing cares about the structure of the measurement and keeps the population pinned, while mere dephasing would just wash out the visible oscillations while still allowing irreversible drift. This distinction matters because it draws a clean line between wrecking a system with random kicks and stabilizing it with informed questions, and the latter is the basis for techniques that hold a quantum bit in a chosen state for longer than passive isolation would allow. Push into the realm of real-time control, and the story becomes almost cinematic. By monitoring the telltale fluorescence of an atom that occasionally goes dark when it hides in a metastable state, experimentalists learn to predict when a jump is about to happen and to apply a precisely timed pulse to reverse it, a catch-and-steer protocol that turns Zeno's freeze into Zeno's shepherd, preventing an unwanted transition rather than merely hoping it won't occur. On integrated platforms, continuous readout lines coupled to qubits let control systems perform a similar dance, watching for the first hint of a drift and correcting it before it grows, a marriage of measurement and feedback that stretches coherence times and brings quantum processors closer to useful scales. Beyond devices and demos, there is a philosophical sweetness to the rule that observation changes what's possible next, not as a mystical claim about mind shaping reality, but as a clean, testable statement that information has physical consequences, that making a record about a property privileges that property's future, and that ignorance and knowledge are not symmetric in a world where the act of knowing leaves a mark. it would be easy to overgeneralize. No, staring at a macroscopically boiling pot won't halt steam. But at the scale where possibilities overlap and interfere, carefully timed questions are as real a force as a gentle push. And by tuning how often and how precisely we ask them, we can write timelines where an atom is kept waiting, a photon is kept circling, or a fragile superposition is kept intact, long enough to be useful. Perhaps the most practical takeaway is an ethic of finesse. To steer quantum systems, you don't always need stronger fields or colder temperatures. Sometimes you need better questions asked at kinder times, because at tiny scales the future is a negotiation, and your measurement apparatus is a party at the table. And if you want one last image to carry out of the lab, picture a metronome that would freely sway from left to right. Then imagine tapping it so frequently and so lightly that it never quite leaves center. The tap is the measurement, the hesitation is the Zeno effect, and the music you make from that poised stillness is a new kind of control, where watching is not passive but a quiet hand that can, for a while, keep change from happening. Two places at once until you look. You can watch a pattern paint itself one dot at a time from particles that never meet, and the first time you see it, your common sense buckles. A faint beam sends single quanta toward two tiny openings. Each quantum lands as a sharp speck on a screen, and yet after many such lone arrivals, a delicate banded image, the hallmark of waves, emerges from the dust, as if every particle consulted a ghostly copy of itself that went the other way. Start with the cleanest version. A source is dimmed until photons leave one by one with long pauses between. Detectors confirm there's never more than a single traveler in flight, and still the tally of impacts grows into bright and dark stripes, where arrivals are common or rare, the more here, less there. Signature of constructive and destructive interference that would be easy to accept if we flooded both slits with water. But here, each dot is a particle hitting once, a local event that somehow respects a global wave pattern. The experiments are wonderfully concrete. Electrons have drawn these fringes with biprisms. Neutrons have done it across meter-long flight paths, and even bulky molecules like carbon, buckyballs, and larger organic clusters have left wavy fingerprints when cooled and launched gently, so their internal jitters don't smear the effect. So the story you're meeting is not a loophole of light but a rule of matter. At small scales, everything travels as a spread-out possibility that can explore alternatives in parallel and reunite with itself to interfere. The rule has a sharp edge, though. The moment you set up a reliable way to learn which slit the particle took, the stripes wash away and the landing pattern becomes a simple sum of two single-slit splashes, as if the world refuses to grant you both a path story and a wave picture at once. This is not about human attention. It is about information existing in the world at all. If the particle leaves even a whisper of path tag on its environment, a stray photon scattered from one slit, a tiny charge pickup in a nearby probe, a vibration in the supporting frame, then the two alternatives stop being perfectly indistinguishable, and the interference fades in proportion to how well you could, in principle, tell them apart. You can test this trade by design. Insert faint, deliberately imperfect which-way markers, tiny polarizers that rotate light differently behind each slit, or spin flips for atoms on one path but not the other, and watch the contrast shrink smoothly rather than snap off, proving there is a continuum between crisp wave fringes and clear path knowledge, a balance that says the sharper your path story, the blurrier your stripes and the sharper your stripes, the vaguer your path story. You can also do the opposite. Make the two paths look distinguishable, then arrange a quantum eraser that erases the path tag before detection, and the fringes reappear in the right subsets of the data. Not because you rewrote history, but because you restored indistinguishability at the only moment that matters for interference, the moment the probability waves reunite. None of this requires mystical language if you hold the right pictures. Imagine each particle launched as a packet that fans through both openings, accumulates a travel history in its phase like a hiker counting steps, and then overlaps with itself on the far side. Where two histories agree, arrivals are frequent. Where the step counts cancel, arrivals are scarce. But any side interaction that can, even in principle, read those counts spoils the overlap. As if an eavesdropper turned the two humming voices into separate, unsingeable tracks. To keep fringes sharp, you must protect the overlap, which is where mundane laboratory craft becomes profound. The source must be quiet, so successive quanta share a stable rhythm. The slits must be clean and still. Stray light must be banished. Air currents and thermal drift must be tamed. And for massive molecules, you often cool, filter velocities, and use gratings etched with painstaking care so their wave-like spread survives the journey. It's easy to confuse this with blur, so here's a crucial distinction. The spots are never smeared. Each detection is a crisp here. But the distribution of many such heres sketches a pattern you can't predict shot by shot. The laws give you a lottery map, not a ticket, and the map's ridges and valleys are what the wave story gets exactly right. That lottery map is technology now, not just a curiosity. Matter wave interferometers that split and recombine atomic packets measure gravity, rotations, and tiny forces with breathtaking sensitivity, using the same two paths, one reunion idea to make fringes slide when the world nudges one arm more than the other. Tilt the apparatus and the pattern shifts. Let Earth's pull bend one root slightly more and the stripes slip. Turn the table and the Sagnac phase announces your spin. In electron microscopes, a beam's coherence, the ability of portions of the wave to stay in step, sets how finely you can resolve structure. And clever biprism setups exploit interference to boost contrast at scales where classical optics would struggle. Even in nanofabrication, interference from electrons or atoms can write patterns beyond limits that simple shadowing would allow. There is a temptation here to smuggle in familiar phrases. The particle knows. The particle travels both paths. But the experiments teach a better humility. Between source and screen, what evolves is not a marble or a fog, but a rule for assigning likelihoods that is wave-like when alternatives are indistinguishable, and particle-like when a record forces a choice. And your decision to install or remove any such record is as much a part of the apparatus as the slits themselves. If you want to test your intuitions, play with variance. Widen one slit and narrow the other to make a faint comb riding on a broad envelope. Shake one slit gently and watch the fringes blur as if the world breathed on the phase. Put a medium in one path to slow its wave and see the bright bands march sideways. Turn the beam down to a few counts per second or less and feel the patience required to watch a ghost image congeal from nothing but single clicks. The slow birth of order from chance. None of this repeats other quantum surprises we've met. It isn't freezing change by checking, nor tunneling through barriers, nor storing light in atoms. It's a specific lesson about complementarity. The availability of path information and the visibility of interference are two ends of a rope you can pull, and your setup decides which end you hold. That rope runs into the real world of noise and heat where perfect isolation is impossible. And there the name is decoherence, the slow leakage of path tag to the environment, which explains why you don't see a tossed baseball interfere with itself. The air, the light, and the ball's own internal chattermark which history happened long before two alternative routes could reunite. Yet at the right scales and temperatures, and with careful hands, you can keep the rope slack long enough to let even heavy molecules sing with themselves, a reminder that classical certainty is not fundamental but emergent, the stable rumor that spreads after too many witnesses pin down the story. And when you step back from the bench, there is a calmer lesson to carry. The world does not always reward a demand for details. Sometimes the very act of asking for a path erases the pattern you hoped to admire. And wisdom, in physics as in life, can be the art of choosing which questions to ask, and when to let two possibilities meet without forcing a confession, so that a deeper picture has space to appear, dot by patient dot. Two particles, one fate across space. You can separate two tiny systems so far apart that a light signal would take years to cross the gap, and still watch their measurement results arrive, with a coordination that makes hidden handshakes feel like the only sensible explanation, until experiments rule those out and leave you with a cleaner, Stranger truth, entanglement is not a message or a wire between particles. It is a shared description that refuses to split into parts. So when you reveal one side, you also reveal how the other must look if measured the same way, no matter the distance. Begin with the picture, not the equations. Imagine creating a pair in a single act. 2 photons born from one decay, 2 ions kicked from one parent state, 2 electrons interacting and then flying apart, and arranging things so that neither photon, ion, or electron has a definite property by itself. Only the pair has a definite relation like always opposite when checked along the same axis, or always the same when checked along any one of several match settings. If you measure your half along a chosen direction, your result is random in isolation, yet if a partner across the lab, across town, across a mountain, measures theirs along the same choice, their result will be perfectly correlated with yours, even though there was no chance to exchange a plan after the settings were picked. The obvious escape route is to imagine the pair carried pre-written answers for all possible questions, like test takers who memorized a full answer key before sitting in separate rooms. But Bell's insight was to show that no stack of locally pre-written answers can reproduce the strength and pattern of correlations that quantum theory predicts, and crucially, that you can test this with real apparatus by choosing measurement settings on the fly and comparing the statistics. For decades, experimenters tightened every loophole. First with photons to close the communication gap between fast setting changes and detection, then with trapped ions and neutral atoms to close the detection gap by catching nearly every event, and finally with cleverly spaced setups that did both at once, loophole-free tests where random number generators selected settings so quickly that no subliminal signal could coordinate them. And the results violated the limits set by any local pre-written plan. They even pushed the free choice concern further back by using light from stars or quasars as cosmic coins to pick settings, so that any conspiracy would have had to begin before the light left those sources, ages ago. A satisfying way to say, if the universe is faking this, it's been planning since long before we were here. The key restraint that keeps all this from turning into faster-than-light messaging is the no signaling rule. The marginal statistics on your side never budge from perfect randomness no matter what choice the remote partner makes, so you cannot encode a 1 or a 0 by twiddling their knob. Only when you later compare notes do the correlations leap into view, and that comparison must follow ordinary channels bound by the speed of light. This is not a rhetorical dodge but a structural feature. Entanglement is strong correlation without usable control. A kind of coordination that only shows itself in hindsight when data are matched, and that is exactly why it can coexist with relativity without contradiction. If you worry that correlation without cause sounds slippery, remember that we have a precise operational meaning. For certain patterns of measurement choices and outcomes, the observed numbers cross a line no local story can cross, and that line has been crossed many times in independent labs, with different particles, devices, and distances. From a practical point of view, this defiance of local common sense is a resource, not just a curiosity. If 2 labs can produce entangled pairs and test a Bell violation between them, they can certify that no eavesdropper could possibly know both sides' outcomes, because any attempt to share the information locally would have suppressed the very correlations the labs observe. That logic leads to device-independent randomness, where the mere fact of violation functions as a receipt that the bit strings you drew are truly unpredictable to any outside observer, and to quantum key distribution schemes where secret keys are distilled from entangled pairs with security, that rest not on assumptions about a hacker's computational power, but on the structure of the physical world. Teleportation, the version that matters, state, not stuff, leans on entanglement in a different way. If you and a partner share an entangled pair, and you perform a joint measurement between your half and an unknown state you want to send, the outcome, together with 2 ordinary bits sent over a classical link, tells your partner how to rotate their half so that it becomes an exact copy of the state you held, while your original is irrevocably consumed in the process. No faster-than-light transfer occurs. The classical bits enforce the speed limit, and nothing material flies through the entangled channel. Yet the identity of the state hops across space, which is why teleportation sits at the heart of quantum networks. It lets fragile states move between nodes without dragging them through noisy channels. When a network needs to span longer distances than a single pair can tolerate, you can perform entanglement swapping. Entangle A with B and C with D, then make a special joint measurement on B and C. And as if by accounting magic, A and D end up entangled despite never touching, a relay trick that underpins designs for quantum repeaters. All of this depends on keeping entanglement alive in a noisy world where warm environments and unshielded fields pull at quantum relations until they unravel, a process called decoherence. So labs go to careful lengths: cryogenic temperatures for solid-state qubits, ultra-high vacuum and laser cooling for atoms, low-loss fibers or satellite links for photons, and error-correcting codes that spread information across many physical carriers so that a few scars can be healed. The same sensitivity that makes entanglement delicate also makes it powerful for sensing. If you prepare many particles in just the right global relation, you can measure phases or fields with precision beyond the ordinary shot noise limit. An edge that shows up in atomic clocks and magnetometers where entanglement is engineered briefly to squeeze uncertainty in the quantity you care about. Turn from 2 particle stories to 3 or more, and the landscape diversifies in ways that classical intuition can't neatly file. Triplets can be entangled in patterns that cannot be reduced to pairs, giving rise to all-or-nothing contradictions with local realism, where a single run of synchronized measurements reveals a conflict rather than slowly building a statistical case. While other forms of non-classicality, like steering and contextuality, show that even the idea a system carries definite properties independent of how you probe it fails in certain structured tests. Entanglement also carries a monogamy rule that feels like gossip with laws. If 2 systems are maximally entangled, neither can be strongly entangled with a third in the same way, a constraint that shapes network design and also clarifies why quantum encryption keys can be private. If you and your partner's correlations are as strong as physics allows, an eavesdropper's must be weak. The philosophical temptation, upon seeing all this, is to say that measurement here changes something there. But the safer, experimentally grounded way to speak is this: before any local revelation, the pair lacks separate identities, and when you perform a measurement, you carve a slice through the joint description that fixes compatible facts on both sides at once, without sending a usable signal. That is a subtle shift of mindset, from things with properties to relations that become properties when asked the right, coordinated questions. And while that language can feel airy, it pays rent every day in fiber links that distribute entanglement across campuses, in satellite experiments that share pairs between cities, in foundries that pattern nanostructures to catch and interfere single photons on chips, and in protocols where the numbers written in our notebooks obey stronger than classical constraints that auditors can check. If you need an image to carry away, picture 2 coins minted in a single press and thrown to opposite sides of a field, each landing heads or tails at random, but arranged so that whenever both tossers choose to check them in the same peculiar way, their outcomes agree or disagree more strongly than any pre-programmed coin could manage. The agreement shows up only later when the tossers meet and compare logs. And because the pattern surpasses any local script, it certifies that no hidden list under either coin could have explained it. Now swap coins for photons or ions, tossers for labs, and peculiar ways for different measurement settings, and you have the skeleton of every entanglement test. The closing comfort is this: entanglement isn't spooky if you stop asking for a picture that never existed. Tiny carriers hauling pre-written answers, and let go of the demand that the world be assembled from independent parts with independent stories. Instead, You accept that sometimes the smallest reliable unit of description is a pair or a web, and that knowledge, when gained in one place, fits into that web so tightly that distant pieces fall into place without anyone pushing them. Between that humility and the engineering grit of real devices lies a new common sense. Not the local kind we grew up with, but a networked kind in which relations are first-class citizens, and two particles, one fate across space, stop sounding magical and start sounding like a rule you can build with, protect, test, and most of all, use. The vacuum has weather. You picture emptiness as silence, but nature's quiet comes with a hiss. The vacuum has weather, a fine-grained jitter of fields that never quite sits still, and you can catch its breeze not with poetry but with instruments. It nudges electron orbits, tips the timing of atomic clocks, seeds the spontaneous glow of excited atoms, and sets hard limits on how perfectly we can measure anything at all. The simplest place to see the forecast is hydrogen, the atom we teach first because it seems so clean, where two levels that old theories said should overlap do not. One sits a little higher, a tiny offset called the Lamb shift, that comes from the electron dancing in a sea of electromagnetic fluctuations, sampling an ever so slightly different potential near the nucleus than far from it, a difference measured in radio frequency slivers yet big enough to rewrite textbooks. That shift is not an afterthought. It's a signature that empty space carries structure, that even with no real light present, the field is restless, and that this restlessness polarizes the vacuum around a charge just enough to tug energy levels by a calculable amount. Once you accept that there is always a background murmur, a cascade of other mysteries falls into place without drama. An excited atom does not emit a photon because it gets bored. It emits because the vacuum itself offers a faint, omnipresent nudge. There's always a little kick, a set of modes ready to accept energy, and if you change those modes, the decay changes. Put the atom in a resonant cavity that emphasizes some wavelengths and suppresses others, and its lifetime stretches or shrinks. An effect engineers call per-cell enhancement or inhibition, depending on whether you fatten or starve the relevant vacuum channels. In the strongest versions, where a single atom or artificial atom is trapped between highly reflective mirrors, the empty cavity splits the atom's line into two peaks, vacuum Rabi splitting, because the atom and the vacuum field hybridize into joint states that swap excitations back and forth, a duet written by nothing more than a tuned emptiness. Even in free space, the vacuum's grain shows up as what we call spontaneous emission noise, shot noise, in photodetectors and amplifiers, the random graininess that persists no matter how carefully you build. Because the field comes quantized in packets, and the zero-point fluctuations keep stirring the pot. If you try to measure a mirror's position with light so gently that you think you could be invisible, the vacuum still pushes back. The fewer photons you use, the more each one's randomness matters, and the jitter they impart is the standard quantum limit that sets the baseline for sensors, from nanomechanical cantilevers to massive gravitational wave observatories. The vacuum's weather is not an enemy here so much as a landscape to navigate, and clever people have learned to shape it. By injecting a special kind of light with noise squeezed out of one variable and into its partner, you can lower the fluctuation you care about at the cost of raising the one you don't, and detectors the size of cathedrals now borrow this idea. Squeezed vacuum states, to hear ripples in space-time from black hole mergers more clearly than they otherwise could, literally improving our reach into the universe by tidying the emptiness at the interferometer's dark port. Step away from optics, and the same background murmur writes itself into other corners. The electron's magnetic moment differs from the naive value by a tiny fraction, because virtual interactions with the vacuum dress the particle, and that correction has been measured and calculated to absurd precision, a stress test of our core theory that owes its success to counting vacuum's contributions carefully. In solid-state devices, tunneling amplitudes and lifetimes are perturbed by electromagnetic environments that, at low temperature, are nothing but tailored empty circuits. Engineers rewrite the zero-point spectrum with filters and resonators to keep qubits coherent longer, or to make single electron pumps tick with quantized accuracy. If you keep the concept honest, the language of virtual particles is a shorthand, not a literal swarm you could bottle. What matters physically is that fields have allowed fluctuations constrained by energy-time trade-offs and by boundary conditions. And those allow jitters skew probabilities in measurable ways. The boundary story can be told without repeating earlier tales. Imagine not parallel plates, but a single atom approaching a surface. The spectrum of vacuum modes near that surface is distorted, and as the atom's dipole leans into that distorted sea, its levels shift and its decay rate changes, giving rise to tiny forces and frequency pulls that show up in atom interferometers and in the fall of ultra-cold atoms past carefully prepared materials. At microwave scales on chips, engineered metamaterials reshape vacuum modes so thoroughly that qubits coupled to them can be made to emit into one direction but not the other, as if emptiness had been given a preferred lane. If you prefer your weather reports from biology's edge, note that even pigment protein complexes in photosynthetic systems, when cooled and isolated, show signatures that are best explained by treating their environment as a structured bath. Not vacuum, but the same principle of fluctuation sculpting dynamics. What looks like noisy background can channel energy efficiently when the spectrum of that noise matches the system's gaps. And on the other end of the scale, accelerations and horizons teach the most vertiginous version of the same lesson. To an observer accelerating through empty space, the vacuum does not look empty at all, but warm, with a temperature proportional to acceleration in a phenomenon that, while ferociously hard to measure directly, is demanded by the same logic that ties together quantum fields and relativity. What counts as no particles depends on motion and context. The practical thread running through all these vignettes is that vacuum fluctuations are not an exotic garnish. They are built into how devices work and how we set metrological standards, so scientists and engineers live with them, tame them, and sometimes turn them into tools. Atomic clocks account for vacuum shifts when quoting their breathtaking accuracies. Semiconductor lasers tick because gain and spontaneous emission trade energy through a reservoir that includes vacuum modes. Superconducting amplifiers ride the line between adding as little noise as quantum mechanics allows and providing enough gain to be useful. And emerging quantum networks must contend with the fact that line losses do not just erase signals, they hand them to an environment that, even at absolute zero, never fully sleeps. Beware, of course, the temptation to promote the vacuum's jitter to a cosmic cash machine. Free energy schemes crumble under careful accounting, because the same theory that predicts fluctuations also fences what can be extracted. And every real device pays in work to shape boundaries, in heat to maintain conditions, and in information to control states. The honest wonder needs no hype. We learned that the simplest atom is subtly displaced by emptiness, that spontaneous processes are encouraged by a quiet audience, that the best sensors are limited by the same background they exploit, and that by redesigning the stage we can change the play without touching the actors. Philosophically, the lesson is gentle and practical at once. Emptiness is not a blank, but a rulebook, the lowest energy arrangement of fields, whose fine print shows up when you measure carefully enough. And your job, whether you are building a clock, a detector, or a theory of how the world hangs together, is to read that fine print with respect. So the next time you imagine nothing, picture a calm sea with ripples too small to see until you set a leaf upon it. A single atom, a mirrored cavity, a beam splitter, and watch the leaf translate those ripples into motion and timing, slight but faithful, proof that the vacuum has weather and that our instruments, like tiny weather vanes, can turn its invisible breeze into knowledge. Sound can make black holes. You don't need a collapsing star to explore an event horizon. You can build one in a lab from sound. Then watch it behave in ways that echo the most extreme predictions of gravity, including a faint thermal whisper that mimics Hawking radiation. And the magic hides not in speculation, but in a simple idea. If a fluid flows faster than those waves can move, there is a one-way boundary where disturbances can go in but not out, a sonic point of no return. Picture a smooth flow in a channel shaped like a nozzle so that upstream the fluid is subsonic. Ripples can travel both ways, but downstream, at the throat, the flow accelerates past the local speed of sound, and from that point on, any wave launched against the current is swept backward, exactly as light inside a black hole cannot climb outward because space itself is flowing inward too fast. This analogy, first made crisp by theorists who noticed that small sound excitations in such flows obey the same kind of equations as light in curved spacetime, gives you a practical recipe for dumb holes. Create a region where the flow outruns the waves, then let the interface between subsonic and supersonic regions stand in for a horizon. The really bold claim is that horizons of any kind should glow faintly with a thermal spectrum set by the surface gravity, essentially how sharply the flow speed changes across the boundary. And in acoustic setups, this temperature depends on gradients you can dial with pumps, lasers, or magnetic fields, turning a cosmic constant into a laboratory knob. Because the predicted signal is tiny and the world is noisy, different platforms attack the problem from different angles. In water tanks, a carefully driven current over a bump creates a horizon for shallow water waves and lets you study how waves transform when they hit it, how incoming ripples split into transmitted and reflected components in a pattern that mirrors the mixing of modes near real horizons, while in optical fibers, a moving refractive index front plays the role of a flowing medium, making light pulses see a horizon that shifts their frequency the way a gravitational field would. And in Bose-Einstein condensates, ultra-cold quantum fluids where sound moves at millimeters per second, you can sculpt a step in the effective potential so that the superfluid flows supersonically past a point, forming a clean, quiet acoustic horizon where the relevant phonons live and where quantum effects are not drowned by thermal agitation. These condensates have delivered some of the most suggestive data by imaging density ripples on either side of the horizon and correlating them. Experimenters have reported pairs of excitations whose statistics and entanglement match what the Hawking picture predicts. A partner mode inside the supersonic region and a Hawking mode outside, born together from the horizon's quantum vacuum, with a spectrum that, within experimental limits, looks thermal at the temperature set by the gradient. Crucially, this isn't heat from friction or an artifact of a pump, but a conversion of zero-point fluctuations into pairs, the same mechanism Hawking's argument uses, translated into the language of sound. Details matter, and they're where the analogy grows teeth. Because real media are dispersive, wave speed depends on wavelength. Short wavelength phonons behave differently than long ones, and this lets you probe a version of the trans-Planckian problem in a safe setting. Remarkably, the thermal character of the radiation persists across a wide range of dispersive behaviors, suggesting that the glow is a robust feature of horizons and not a fragile idealization, an encouraging message if you hope Hawking's reasoning survives the messy physics near actual black holes. The lab lets you push further than nature easily can. By creating a neighboring white hole horizon, you can trap phonons between a black and a white horizon and build a black hole laser, a cavity where the pair production process feeds itself and amplifies, turning a barely measurable trickle into a booming, structured signal whose spectrum and growth rate test the underlying mode conversion rules. Rotate the fluid and analogues of superradiance appear, waves that steal energy from a vortex the way light should from a spinning black hole, offering another handle on horizon physics through gain, not just through glow. Other tabletop setups let you nudge the horizon's profile and watch how the temperature follows the gradient. Check how added turbulence or disorder masks or mimics the quantum signature, and switch between stimulated and spontaneous regimes, where you seed the process with a known wave and examine how it emerges transformed. The hardest part is always the same, ruling out mundane noise and classical amplification, which is why the strongest claims lean on correlations that have a quantum fingerprint, specific patterns between inside and outside modes that cannot be faked by simple thermal jitter, and on reproducibility across platforms that share only the horizon mathematics. Beyond the thrill of seeing a famous prediction come to life on a benchtop, these analogues pay back in technique and insight. They give us tunable, visual arenas to watch quantum fields in curved backgrounds, something the cosmos itself makes hard because real black holes are distant. Their Hawking emission is unimaginably faint against the cosmic microwave and astrophysical fog. And by the time a black hole's glow would be hot enough to detect, it would be too tiny to survive the noise of its environment. In condensed matter language, horizons are just interfaces where wave modes get mixed by a flow, and the lesson slices cleanly across fields. Whether you're building a precision sensor or a quantum network, boundaries and motion can convert background fluctuations into particles, and you can either fight or exploit this by shaping gradients carefully. Philosophers sometimes worry that an analogy might hide gaps, so it's worth stating plainly what these experiments do and do not show. They do not create gravity or bend space-time, and no signal outruns a speed limit because the light cone here is the sound cone set by the medium. But they do realize the same mathematical structure that makes Hawking's argument tick. They do measure spectral features and correlations that the argument predicts, and they do let us test how robust those features are in the presence of dispersion, dissipation, and finite size. Three realities that any honest theory of real horizons must confront. Perhaps the quietest payoff is pedagogical and moral at once, when you can stand at a tank, a fiber bench, or a cryostat and watch a horizon's one-way logic sculpt waves. The idea of an event horizon stops being myth and becomes a device, a thing you can dial, reshape, and question. And once a grand concept can be questioned gently, it becomes yours. So the next time someone says black holes only belong to supercomputers and telescopes, remember the lab scenes where a gradient does the work of gravity, where a horizon hums in a cold vapor, and where pairs of tiny ripples flicker into existence and slip apart on either side of a line that sound cannot cross. A human-scaled theater for a cosmic idea, teaching us that sometimes the shortest path to a far frontier is to rebuild its rules, patiently, in miniature. And listen, lasers can chill atoms to a crawl. Imagine slowing a hummingbird mid-wing beat without touching it. Laser cooling does something even quieter to atoms, turning frantic thermal motion into a slow drift until matter hangs just shy of absolute zero. And the elegance of it lies in using light not as heat, but as a brake that only pulls when an atom moves the wrong way. The trick begins with the Doppler effect you already know from the changing pitch of a siren, except now it's color that shifts. If a laser is tuned a hair redder than an atom's favorite absorption color, only atoms flying toward the beam see that color Doppler shifted back into resonance and absorb a photon, getting a tiny momentum nudge opposite their motion, while atoms drifting away are farther from resonance and mostly ignored. So a single beam acts like a one-way headwind. Cross three of these red detuned beams in each spatial direction, and the atom feels a viscous drag no matter where it tries to go, a translucent optical molasses that can drop temperatures from room values to a fraction of a millikelvin in thousandths of a second, limited by a balance between cooling kicks from absorbed photons and random recoil from the photons re-emitted in all directions. Because gravity still pulls, experimenters add a magnetic field whose strength changes across space and shine in another set of beams, so that atoms are always tuned into resonance when they stray from center, which creates a spring-like restoring force in addition to the molasses drag. This is the magneto-optical trap, a workhorse that gathers millions of atoms into a glowing, floating cloud smaller than a raindrop, poised for more refined cooling. If the story stopped there, Doppler physics would set a flaw. The temperatures where the cooling force and the heating from random re-emission balance, but clever use of atomic structure lets you slip under that limit by arranging light with carefully chosen polarizations and intensities to build a landscape of bright and dark zones. Atoms climb hills where they are optically pumped into states that couple less to light at the top. Then they roll down and get pumped back into states that love light again at the bottom, losing energy on each cycle like a patient Sisyphus who, for once, is allowed to rest lower than he started. This polarization gradient, or Sisyphus cooling, routinely reaches microkelvin and below, and by shutting off the molasses suddenly, the expanding size of the cloud acts as a thermometer. The colder the sample, the slower the expansion, a direct image of temperature drawn in space. for ions held aloft by electric fields in ultra-high vacuum. A related approach called resolved sideband cooling uses narrow-band lasers to pluck energy specifically from quantized vibrational steps of the trapped particle, walking the ion down rung by rung to its motional ground state until the only motion left is quantum jitter. Neutral atoms can be tamed by another cousin method, Raman sideband cooling, which uses two laser colors to move population between internal states while pulling away a precisely chosen chunk of kinetic energy, stitching together state changes and momentum changes like a tailor taking in a seam. All of these methods share the same moral. Light can be sculpted into a tool that takes energy away while keeping the atom's identity intact, cooling translational motion without fraying the internal state you care about. Once atoms move at centimeters per second instead of hundreds of meters per second, whole technologies wake up. Atomic fountains toss ultra-cold atoms upward to drift through microwave or optical fields with minimal blur, stretching the tick of atomic clocks and pushing timing accuracy to parts in 10^18. The level we're climbing a few centimeters changes the rate measurably, and tiny frequency shifts from blackbody radiation or stray fields must be accounted for. Atom interferometers, which split and recombine matter waves like miniature double-slit experiments on a chip, use those long, quiet drift times to measure gravity, rotation, and subtle forces with startling sensitivity, from surveying underground voids to sniffing for new physics in how free fall treats different elements. Cold atoms assembled in optical tweezers and lattices, arrays of microscopic traps made from light itself, become reconfigurable crystals for quantum simulation, where researchers dial interactions to mimic hard-to-solve materials or model exotic phases of matter, and watch phase transitions unfold atom by atom, frame by frame. In the same traps, entangling gates between selected neighbors turn neutral atoms into qubits for quantum computing, while trapped ions cooled to the ground state form some of the cleanest logic elements we know, their motions so well controlled that a single stray photon can be flagged as an error. Laser cooling's reach even extends to molecules, once thought too complicated because their many internal modes offered too many ways to leak energy. By choosing special species with nearly closed optical cycles, adding repump lasers to plug the leaks, and choreographing polarization and frequency ramps, teams have coaxed polar molecules into the microkelvin regime, opening doors to precision tests of fundamental symmetries and to quantum chemistry, where reactions are guided by design rather than by luck. Every step down the temperature ladder demands stricter quiet. Background gas must be pumped away until a particle can fly for minutes without collision. Blackbody radiation from warm walls must be tamed, and magnetic and electric fields must be smoothed until their ripples are smaller than the shifts they would cause. At the very bottom of the ladder, after laser cooling has done its best, another classical tool takes over, evaporative cooling, in which the hottest atoms are allowed to escape from a magnetic or optical bowl, and the remainder rethermalize colder, exactly like letting steam carry heat out of a cup of tea, except here, the steam is the tail of a velocity distribution, and the reward is crossing into a domain where waves of matter synchronize. Bose-Einstein condensates, delicate pools where thousands of atoms occupy the same quantum state and flow without viscosity through narrow channels. It is tempting to call these samples motionless, but honesty is better. Even at nanokelvin temperatures, atoms cannot sit perfectly still because quantum mechanics forbids it, leaving a residual recoil limit set by the jolt each photon delivers and a floor imposed by the spreading of the wave packet itself. Engineers do not despair. They squeeze uncertainty into components they don't mind and shape pulses so that heating channels are starved, achieving stabilities and coherences that let clocks compare time across continents. And gravity experiments resolve the tug of underground aquifers filling after a rain. The safety valve in this story is that cooling with light never violates conservation laws. Each absorbed photon takes momentum from the beam, and each emitted photon carries it away in random directions. So the atom's net energy drops by exactly the imbalance you engineer with detuning and geometry. A bookkeeping so strict that a mistuned laser simply heats instead of cools. In the lab, you can see the difference with your own eyes. The trapped cloud tightens, dims, and then as you push too hard or forget a repump, it smears and vanishes. Proof that this is not a metaphor about calm. It's a procedure that wins or loses by measurable margins. Step back from the apparatus, and the deeper lesson is surprisingly humane. You don't always need to force a system colder with brute refrigeration. You can make its preferred interactions work for you by choosing when and how to offer energy, so that decline, not agitation, is the path of least resistance. From the whisper of a red detuned beam to the silent hover of a ground state ion, lasers can coax matter down the ladder of motion until time seems to slow inside a glass cell or a vacuum chamber. Not because the world has changed its rules, but because we learn to use them. And in that slow air, new instruments and ideas have room to breathe. Clocks that redefine second by second what accuracy means, sensors that hear the planet shift underfoot, and tabletop quantum systems that let us ask questions once reserved for stars, all made possible by light that learned to be a gentle hand rather than a flame. Space expands faster than light. You grow up with a simple rule: nothing outruns light. So it feels like a cheat when astronomers say distant galaxies recede from you faster than any beam could chase. But the rule stands once you swap a racing mindset for a stretching one. Special relativity governs how fast things can move through space, while cosmology often cares how fast space itself grows between things. And that second kind of speed can exceed light without letting messages jump the queue. Begin with a picture you can carry in your head. Sprinkle dots on a stretchy fabric. Call them galaxies that mostly keep to their own neighborhoods. And now pull gently on all sides so every patch grows. No dot is pushing past its local neighbors at forbidden speed. Yet the distance between far apart dots grows quickly because each little stretch adds to the next. And over sufficiently long chains, the total can beat light without any dot breaking a local limit. The universe behaves like this fabric because on large scales it is well described by a smooth, expanding geometry where a single quantity, the scale factor, tells you how big a comoving ruler becomes with time. And Hubble's observation that recession speed scales with distance is the observational echo of that rule. Double the distance, double the rate at which the space between you and that galaxy increases. The crucial honesty is that recession speed here isn't a rocket velocity you could measure with a radar gun in a single flat arena. It's the rate at which the proper distance between two stationary in the cosmic sense points changes as the underlying metric swells. Because relativity's speed limit applies to signals inside each tiny local frame, causality is safe. No one uses the metric's swelling to send a bit instantly across the cosmos, so the universe can maintain both truths at once. Locally, nothing outruns light. Globally, distance can grow faster than light because the yardsticks themselves are lengthening everywhere. This reframes several confusions at once. When we say distant galaxies race away faster than light, we do not mean they cut through the space around them at illegal speed. We mean that the chain of expanding patches between us and them accumulates so quickly that the proper distance increases faster than a photon could close if the yardstick stopped growing. Equally, when we speak of the observable universe, we don't mean a hard shell beyond which nothing exists. We mean the region from which light has had time to reach us, given the entire expansion history. A history that includes epochs, when the universe slowed, and epochs when it sped up. So our horizon is a time boundary as much as a distance one. This is why you can currently observe galaxies whose present-day recession speeds exceed light. The photons we detect left them billions of years ago, when they were closer and the fabric was stretching at a different pace. And those photons slipped from patch to patch, sometimes losing ground, sometimes gaining as the Hubble rate changed, eventually making it to us. The same story explains why there are regions we will never influence, no matter how long we wait. In a universe where dark energy drives a long-term acceleration, there exists a cosmic event horizon, a distance beyond which light emitted today will never reach us, because the expansion keeps adding more space faster than the photon can traverse newly minted room. This horizon is not a wall you can see. but it draws a practical circle around our future conversation partners. The set of distant civilizations we could ever exchange signals with, even if we broadcast forever. You can feel the rule beneath redshift too. The lengthening of wave crests from distant galaxies is not just a Doppler shift from motion through space. It is also a cosmological stretch, because each crest was pulled while crossing the swelling fabric. So the spectrum we receive has been reddened by the accumulated growth of the scale factor along its path. And this is why redshift in cosmology doubles as a time machine. Bigger stretch means earlier, epoch, letting astronomers arrange snapshots into a history that runs from the afterglow of the first light to the sculpted webs of galaxies today. The balloon analogy, often used in classrooms, helps but misleads if you take it literally. Yes, every dot sees every other dot move away as the balloon inflates. And there is no privileged center on the surface. Yet unlike the balloon, our universe's surface is not embedded in a higher room you could point to. An expansion needn't happen into anything. Space is what grows. Likewise, rubber's skin has edges and your breath sits outside it. But the large-scale universe has no boundary we can see and no external air. The point of the analogy isn't to match every detail. It's to loosen your grip on motion through and replace it with distance from in a geometry that changes. To go deeper without symbols, separate three kinds of cosmic distance that often get bundled into one. Comoving distance keeps track of how many stretchable rulers apart two places are, ignoring the ruler's changing size. Proper distance tells you how long a ruler would read if you could freeze expansion and measure now. And horizons convert those abstract lengths into what can be seen or influenced, given the light travel time and the growth rate at each era. These distinctions matter because they cure paradoxes before they arise. A galaxy can sit quietly at fixed comoving coordinates, no thrusters, no wind, and still be carried away so that its proper distance increases superluminally, while a photon's comoving position changes at a pace set by the expansion, sometimes making headway, sometimes stalling against the drift. History now steps in to give this a plot. Early on, the universe likely underwent a brief, breathtaking period called inflation, in which the scale factor sped up so fast that distances ballooned by outrageous factors in a blink, smoothing and flattening the patch we inhabit, and seeding the tiny ripples that later grew into galaxies. Inflation's wild shove pushed regions that were once neighbors far beyond each other's horizons, explaining why the microwave background looks uniform across directions that could never have traded light since then, because they were once in causal contact before the Great Stretch. Later, as matter took over, expansion slowed, letting structure grow under gravity's pull. Later still, dark energy began to dominate, and expansion started to accelerate again, changing the balance of what will forever remain reachable. The Hubble constant that headlines popular articles is the present-day value of the expansion rate, not an unchanging meter, and it has evolved over cosmic time, falling dramatically from its early fever to today's gentler pace. This changing rate is why the naive calculation, divide velocity by distance to get age, only gives a rough sense of the universe's timeline. To get the age precisely, you must integrate the whole history, weighting how fast the scale factor grew at each stage. Even definitions of faster than light deserve careful hands. Recession speeds can exceed light at large distances because they are not local velocities in flat space. Gravitational waves and light still mark the ultimate slope for causal influence, and every real signal respects those local light cones. Engineers building detectors for those waves do not worry that cosmic expansion will let nearby events shout early. They correct for redshift when they infer distances and masses, but the causal structure of each merger unfolds locally and transmits outward at light speed. The practical implications of all this are oddly intimate. When clockmakers compare atomic clocks on different continents using lasers bounced through fibers and satellites, they must account for how the expanding geometry and the planet's gravity shape frequencies and times. When astronomers design deep surveys, they translate a target redshift into exposure times and filter choices, because expansion spreads and dims light in predictable ways. And when mission designers imagine future probes of the cosmic microwave background or galaxy clustering, They aim to measure not just the present rate, but the entire function that tells how expansion has changed, because that curve encodes the properties of dark energy, the most modest name for one of the boldest unknowns. Perhaps the most grounding insight is philosophical and concrete at once. The law you learned as a child was never about banishing the universe's creativity. It was about protecting cause and effect, and metric expansion, however fast, is consistent with that protection. If this softens your awe, let it deepen it instead. You live in a cosmos where the nearest rule and the farthest flow coexist, where the path between islands can lengthen faster than any boat can row, while the water at each oar obeys the same speed limit it always has. The comfort in that image is practical. We can map what we will eventually see and what we will never touch. We can measure the dimming and stretching of ancient light to reconstruct a credible history, and we can accept that the universe's largeness does not insult our rules, but demonstrates their scope. So when you read that space expands faster than light, hear not a loophole but a precise sentence. The yardsticks grow everywhere at once. The sum of their growth can outpace any runner, and yet no message skips a step. Causality stays intact while the distances swell, leaving you with a sky that recedes majestically and a physics that stays honest. Both truths held together by the simple decision to treat geometry as an actor and not just a stage. There's no universal now. You think the world shares a single clock, but the closer you look, the more now behaves like a local custom, perfectly clear inside your neighborhood, negotiable across distance and frame-dependent once motion gets involved. So two events that feel obviously simultaneous to you can, for someone gliding past at high speed, unfold in a different order, not because anyone is mistaken, but because time slices tilt with motion. Start with Einstein's friendly train. Lightning strikes the front and back of a carriage, and a person standing on the platform halfway between the scorch marks sees the flashes arrive together and declares, confidently, they were simultaneous, while a rider rushing forward meets the front flash sooner than the back one and, with the same logic, insists the front strike happened first. Neither observer cheats. Each uses the same rule to sync clocks by light signals and then reasons from those synchronized clocks. But they live in different states of motion. And in relativity, that difference isn't a detail, it's the rule book. The speed of light has the same value for everyone. So to protect that constancy, the universe adjusts our bookkeeping, letting measurements of at the same time and how long between depend on how you're moving. The result shocks only until you see how it's built. To declare distant events simultaneous, you need a way to align clocks spread out in space. And the standard method, send out light pulses, correct for travel time, set dials so signals launched from the midpoint reach the ends together, works inside each frame, but yields distinct alignments for frames sliding past one another, as if the pages of time you use to slice space-time lean at slightly different angles depending on your motion. Because we're wired to trust a single universal present, this feels like a trick, but the universe quietly enforces sanity. If two events can influence each other, if a signal could, in principle, connect them, every observer agrees on their order. Only for pairs separated so widely in space and so narrowly in time that no light could bridge the gap, does the order become a matter of perspective. And those are exactly the pairs that could never be used to build a cause and effect chain in the first place. The practical consequences are everywhere once you start listening for them. In particle accelerators, bunches of protons and electrons must be timed with picosecond care as they chase each other near light speed. And the control system's now is defined in the machine's frame, not in the lab worker's wristwatch. Otherwise, collisions would miss by micrometers that matter. In intercontinental metrology, labs compare ultra-precise optical clocks by trading carefully shaped pulses through fibers and satellites. And the comparison algorithms explicitly account for motion of the endpoints and of Earth itself, because the same moment at two far sites is a convention that must be declared and corrected, not something nature hands you for free. Even in simple data networks, timestamping packets crisscrossing the planet forces engineers to define a reference frame and stick to it, or else events that were simultaneous in one log will drift apart in another. An annoyance in finance, a hazard in distributed control, a puzzle in forensic reconstruction. Unless you understand that simultaneity is negotiated, the effect shows up in moving vehicles at human scales too, though softly. High-speed rail designers and timing systems on aircraft choose a frame to define synchronized onboard clocks, and the small but real differences from ground clocks are part of certification and safety margins. Astronomy offers an everyday example that hides in plain sight. When observatories spread across Earth take data on the same transient flash in the sky, they later barycenter their timestamps, translate them into the reference frame centered on the solar system's mass, so that comparisons aren't muddied by Earth's motion, a bookkeeping chore that only makes sense if you've accepted that now depends on who's moving and how. Push the idea further, and the geometry becomes a guide. Imagine space-time as a grid where your present is a horizontal slice through events. Start moving, and that slice tilts, scooping up some future there and some past here compared with a stationary cut, a picture that resolves paradoxes before they start. No one leaps into anyone else's causal past, but the notion of a single universal present dissolves in favor of many valid, overlapping presents stitched together by agreed protocols when we need to compare notes. Even the way we talk about long baselines in radio astronomy, or about coordinating detectors on separate continents, quietly encodes this. Teams speak of time transfer rather than absolute time, of reference epochs rather than the present. If you crave a hands-on feel for the rule, try this thought experiment without equations. Set up synchronized clocks along a straight road using the standard light pulse method, then ride past on a smooth cart and perform the same procedure in your moving frame. When you pass a particular roadside clock, you'll agree on its reading at the instant you're abreast, but you won't agree on what the far clocks read at that same instant. And the difference scales with both your speed and the distance to those clocks, producing a mismatch that isn't a calibration error but the expected, testable offset from relativity of simultaneity. Laboratories have verified this logic with flying atomic clocks, with fast ions emitting light whose phases encode time, and with resonant cavities carried on moving platforms, each confirming that distant clock alignment is a convention glued to a frame, not a universal decree. If you worry this makes planning or morality slippery, how can we coordinate if we don't share a global now? Take comfort in the fact that physics gives you tools rather than anxiety. Choose a frame suited to your task, declare it openly, and transform to others when needed. The transformations are not compromises, but precise translations that preserve cause and effect, and let different teams reconcile their records without contradiction. The deeper human lesson is gentle. Much of our impatience comes from expecting a single clock to rule every perspective. Yet the world we inhabit runs on agreements, about time zones, about calendars, about when a day begins, and relativity simply extends that humility outward, reminding us that across distance and speed, even the present tense has dialects. Hold that thought the next time you watch lightning flicker on a storm's distant edge, or follow a live broadcast that arrives a split second apart on two screens. Part of the mismatch is technology, part is geometry, and hidden inside is a truth as steady as any law. There is no universal now, only local nows that we weave into a coherent story when we meet and compare. And once you accept that, the sky doesn't become less real. It becomes more intelligible, a place where time is not a single rail but a mesh of tracks, each straight in its own map, all intersecting honestly where paths cross. Information has weight. You think ideas are weightless, but try to truly delete one, and the room gets a little warmer. Every time you reset a bit from "I don't know" to a chosen value, you pay in heat, a tiny toll that nature always collects. And once you see that information has a thermodynamic price, daily technology and old philosophical puzzles fall into a single ledger where memory, order, and temperature share the same bookkeeping. Start with the most ordinary act. You clear a file, empty a cache, factory reset a gadget, and deep inside, circuits push voltages into a definite state, stripping away alternatives so the device can forget, and that Narrowing of possibilities is not free. At any non-zero temperature, there is a minimum energy that must be released as heat for each bit you force into a known value, roughly the product of Boltzmann's constant, the ambient temperature, and the natural logarithm of 2. A mouthful you can translate as a fixed whisper of warmth per bit at room conditions, no matter how clever your engineer is. Moving or copying a bit, in principle, can be done without this fundamental cost if you avoid loss and keep track of the full microstate. But true erasure, collapsing many possible states into one, throws information away, and the physics that governs gases expanding, ice melting, and batteries discharging demands you pay for that reduction in uncertainty by raising entropy somewhere else, which in a computer means the chip, the socket, the air. This is the quiet resolution of Maxwell's demon, the impish sprite from 19th century thought experiments who seemed to harvest free energy by letting only fast molecules pass a door. The trick fails because the demon must store and eventually erase records of its decisions, and when it cleans house, it heats the world by exactly the amount needed to keep the second law honest. This is not armchair reasoning. Labs have measured the cost by building single-bit memories out of microscopic beads trapped by laser tweezers or tiny electronic islands, letting thermal jitters represent unknown, and then performing carefully controlled resets. When the protocol is gentle and slow, the heat released approaches the predicted limit, and when it is rushed or sloppy, the excess cost shows up as additional warmth, a literal, detectable puff of energy that turns a philosophical claim into a thermometer reading. Because most of your devices run many steps above this floor, the limit may sound academic, yet it explains why shrinking transistors and sharpening algorithms can never drive energy to zero as long as you keep erasing. Power scales down, then stops at a wall set by logic itself. It also reframes design choices. Compressing data preserves information in fewer bits, but the final deletion of the leftovers still pays the toll, while caching and memoization trade space for time without inherently adding heat unless you discard the cache. Architects already play chess with this. They keep intermediate results when it saves recomputation. They pipeline work to avoid needless resets. And in the far frontier, they study reversible computing, where gates such as those imagined by Bennett and Fredkin compute without throwing information away, letting the system, in principle, sidestep fundamental heat at the cost of more complex hardware and longer runtimes. Biology has long practiced its own thermodynamic thrift. Enzymes steer reactions along low-loss paths. DNA stores information at astonishing density with error correction that pays a metabolic price. And neurons burn energy both to signal and to reset ion gradients after spikes, the forgetting step that readies a cell for the next thought. So your brain's warmth is not just inefficiency, it is the ongoing cost of clearing registers for fresh meaning. Now zoom out to the infrastructure you rarely see. Data centers move unimaginable rivers of bits, and while copying, routing, and caching can be efficient, the relentless stream of overwrites, discards, and delocations generates acres of waste heat that engineers must shepherd away with fans, fluids, and cleverly placed heat exchangers. Some cities already capture this information warmth to heat homes or greenhouses, a small civic poetry in which deleted photos, expired logs, and retired machine learning parameters become winter comfort. Cryptography and error correction add their own thermal footnotes. To keep secrets or fight noise, you must detect and remove uncertainty, and each correction involves measurements, syndrome extraction, and eventually erasure. So the promise of reliable computation in harsh environments is really a promise to pay the energy bill in a planned, distributed way, rather than at random. The discipline reaches even into your pocket. The reason a phone warms during heavy app churn or when you purge and reinstall is not only wireless radios and displays, it's also the steady drizzle of resets as gigabytes of state are deleted and rewritten, each bit adding its micro-contribution to the palm heat you feel. Knowing this does not condemn innovation to a thermal swamp. It guides it. Better file systems reduce needless overwrites. Streaming formats avoid full rewrites for tiny edits. Log-structured storage defers and batches erasures to minimize peaks. And operating systems design their memory allocators to reuse and recycle state, so the expensive step of true forgetting happens less often. On the scientific edge, people push the limit from both sides. Single-molecule experiments approach the floor to check our deepest assumptions, while cryogenic electronics lower the ambient temperature so the per-bit cost drops, though never to zero. Quantum devices add nuance without overthrowing the rule. Unitary evolution shuffles information without loss, but any measurement and reset in a quantum processor still entails erasure somewhere in the control stack, and careful engineers count those costs right alongside coherence times. For you, the practical wisdom is small and sturdy. Treat deletion as a resource, not an afterthought. Design workflows that keep what they can, summarize what they must, and discard only with intention. Understand that every clear, reset, and empty trash nudges a little heat into the environment, a whisper size but honest price for order, and that civilization's appetite for tidier states, shorter queues, cleaner datasets, snappier apps, will always couple to energy policy. And if there is a soft comfort in this, it is that the world refuses to lie about cost. Meaning is tied to matter, tidiness to temperature, and knowledge to careful stewardship of what we keep versus what we choose to forget. So when you close a tab or finalize a project, remember that the feeling of clearing space is not only psychological, it is physical, part of a long conversation between memory and heat in which every decision leaves a trace. And living well includes learning which traces are worth the warmth. Your memories rewrite themselves. Recall edits the past you think you remember. You trust your past like a photo album, but each time you open a page, your brain quietly edits the picture. Recall is not a replay. It is a rewrite session that keeps what still fits, swaps what conflicts, and sometimes invents convincing filler so the story holds together. And the science behind this is both humbling and useful if you let it change how you remember. When you retrieve an experience, the fingerprinted pattern of cells that encoded it, an engram, reactivates under the guidance of the hippocampus, which acts like a switchboard to pull details from sensory cortices and meaning from association areas. And for a short window after reactivation, that network is plastic again, unusually open to change, a phase called reconsolidation. In that phase, new context, fresh beliefs, and leading questions can be woven into the trace. If the new input reduces the brain's prediction error, the mismatch between what the old memory predicted and what you are now perceiving or told, the nervous system treats the update as an improvement and saves it. Which is why hearing a confident but inaccurate statement right after you recall an event can permanently distort what you saw. Experiments make this concrete. Volunteers who watch a stage scene and then receive subtly misleading information later often recall the inserted details as if they were present from the start. A robust effect that grows when the misinformation arrives during that malleable window, and paradigms that present lists of related words reliably produce false recall of a non-present theme word because the brain stores the gist as eagerly as it stores the particulars. Your confidence, unfortunately, is a poor auditor. Emotional intensity and repetition inflate certainty even when accuracy decays, which explains why flashbulb memories of dramatic public events feel vivid but drift measurably on retesting. At a cellular level, the hippocampus sits at the crossroads of two complementary processes: pattern separation, which keeps similar experiences from overwriting each other by distributing their traces across partly distinct populations, and pattern completion, which lets a fragmentary cue call up a whole scene. And the dynamic balance between them means that similar days are easy to blend while sparse, unusual features are easier to anchor. Stress hormones complicate this balance. Moderate arousal can strengthen memory for central elements, but high prolonged stress narrows attention, tilts storage toward the emotional core, and leaves peripheral details underspecified, which later invites the mind to fix gaps with plausible but invented pieces. Sleep is memory's night shift, and also its editor. During deep stages, bursts of rhythmic activity help the cortex integrate the day's hippocampal sketches into long-term networks, and this consolidation tends to semanticize over time, meaning stabilizes surface, detail thins, so a story retold months later will sound tidier and more thematic than the messy original because the brain has traded texture for structure. Not all edits are additive. Retrieval-induced forgetting shows that selectively recalling part of a category can suppress unretrieved siblings, likely because the network that wins at recall is strengthened while competing traces are inhibited. So every test is also a training session that shapes what future you will find easy to access. Suppression can also be deliberate. With repeated practice, you can learn to interrupt an unwanted memory when it starts, and studies show that doing so over many trials reduces later intrusion frequency, a hint that top-down control pathways can downweight an engram's grip. If the idea of malleable memory sounds like a threat, it is also an opportunity used in therapy. By briefly reactivating a traumatic memory and then introducing safe corrective experiences or certain medications during the reconsolidation window, clinicians can weaken the sting of learned fear without erasing the factual content. And exposure therapies often work by letting the brain discover that the feared outcome does not follow, prompting a rewrite towards safety. Technology underscores how literal this rewritability is. Animal studies that tag and later stimulate or silence specific cell assemblies can cause mice to act as though a memory were present when it was not, or to soften a fear response by rewriting the context associated with it, demonstrating that what we call the memory is a particular pattern whose influence can be tuned. None of this makes eyewitness testimony worthless, but it does insist on procedures that respect biology. Separate witnesses, avoid leading phrasing, record initial accounts immediately, and treat later confidence as suspect unless it is accompanied by preserved, specific detail. In everyday life, the lesson is kinder. If you want accuracy, design habits that reduce the need for reconstructive guesswork. Externalize critical facts to notes or photos taken as close to the event as possible. Timestamp and version them so later edits are visible. And when you must rely on your head, use context reinstatement by revisiting the location, posture, or soundtrack of the original moment, which cues pattern completion more faithfully than abstract recollection. You can also train memory gently by spacing reviews and by testing yourself rather than rereading, because every successful retrieval strengthens the path you'll use next time and reduces the brain's incentive to fill in. If you want to encourage wise forgetting, structure your environment so outdated cues don't keep reactivating traces you no longer need. Archive old threads, clear visual clutter, and let sleep complete what waking hours begin. The philosophical temptation is to mourn the loss of a pristine, camera-like past. But the adaptive view is more generous. A system that rewrites is a system that learns, and the small distortions that embarrass you in trivia are the same flexibility that lets you update beliefs, reconcile contradictions, and weave new lessons into old narratives. The caution is simple and liberating at once. Treat your memories as living drafts, not final editions, and act accordingly when stakes are high, cross-checking with records and with other people's accounts. And if you're looking for a soft landing, take this with you. The self you carry isn't a museum of fixed exhibits, but a library with an active acquisitions desk and a skilled editor who keeps the catalogue useful, even if a few entries merge or shift over time. Knowing this does not cheapen your past. It gives you agency in how you handle it, inviting you to build gentler rituals for remembering, wiser habits for recording, and a generous grace for the ways you and others revise what came before. Your sense of self is a construction. You wake up each morning certain that a single continuous I climbed out of sleep. Yet under the hood, your brain is negotiating, minute by minute, among multiple systems that each claim a piece of you. And the person you feel yourself to be is the tidy outcome of that negotiation, rather than a solitary conductor. Start with the body, because the body is where you gets traction. The brain maintains a constantly updated map of posture, touch, temperature, pressure, and head motion, braided with signals from the inner ear and viscera. And this body model lives in a network that includes the posterior insula, somatosensory cortices, and the temporoparietal junction, regions that combine outside information with internal cues to decide what belongs to you and where you are in space. Disturb the balance and the seams show. Shifts in vestibular input or electrical stimulation near the temporoparietal junction can induce an out-of-body perspective, as if the self's anchor had been loosened. while certain strokes or lesions produce neglect of one side of space or even denial of ownership over a limb, conditions in which perfectly functioning muscles are felt as foreign or absent because the who is where process has lost its vote. Beyond the body map sits a sense of agency, the feeling that an action is yours and not just an event happening near you. And experiments reveal how fragile this is. Tweak the timing between a person's movement and its visual feedback by a few dozen milliseconds, and the brain's estimate of authorship drifts, a phenomenon mirrored clinically when people with specific frontal or parietal damage report that their hand seems moved by someone else, or, very differently, that someone else's action feels triggered by them. Meanwhile, another coalition builds the story of your life, the autobiographical self, drawing on hippocampus for event details and a set of midline hubs often called the default mode network to knit those details into a narrative with motives and themes. And this narrator is resourceful enough to fill gaps when evidence runs thin, which is why split-brain patients whose hemispheres cannot share data directly will sometimes explain a behavior initiated by one side with a plausible tale drafted by the other, convincing, not because it is right, but because the storyteller module is designed to keep the plot coherent. The self that plans sits elsewhere again, in control circuits that include dorsolateral prefrontal cortex and parts of the parietal lobe, regions that hold goals online, inhibit impulses, and choose among options, functions you feel as will and restraint. And these compete constantly with valuation systems deep in the brain that compute urgency and reward. In the middle of this tangle, a salience network acts like a switchboard, deciding when to turn inward to reflect or outward to act. And when its switching falters, people can feel either trapped in rumination or scattered by every nudge from the world. Perception adds another layer to the construction. Your brain aligns sight, touch, and sound on a tight schedule to present one stable scene anchored to the body. And when researchers use virtual reality or prisms to shift these alignments, the felt location of I can be shepherded forward, backward, or to the side without any tissue moving, evidence that the place you inhabit is a consensus map, not an immutable coordinate. Chemistry can also tilt the balance. Under psychedelics, the midline narrative hubs often loosen their coupling, and alternative networks transiently talk more freely, a change people often describe as ego dissolution, while in meditation studies, experienced practitioners show quieter baseline chatter in those same hubs and stronger connectivity between attention, systems and interoceptive areas, correlating with reports of a self that feels less like a commentator and more like a clear vantage. Development tells the same story over years. Infants first master agency at the level of cause and effect, kick and the mobile moves, long before they can recognize themselves in a mirror or tell a story about yesterday. And only later do language and memory knit a durable persona around those earlier sensorimotor achievements. Pathology continues the lesson by subtraction. In Capgras syndrome, the emotional tag that normally accompanies a familiar face goes missing. So a loved one looks correct but feels wrong, and the mind resolves the conflict by positing an imposter, revealing that recognition and this belongs in my life are separable votes. In anosognosia, a person with paralysis may sincerely insist they can move, because the predictive models for action and the signals that would correct them are out of alignment, demonstrating that conviction is not a guarantee of intact checking. Even time inside the self is assembled. Your sense of continuity is a braid of working memory that carries the last few seconds, episodic memory that retrieves titles and scenes from the past, and prospective memory that equips you with reminders for the future. And when any strand is thinned through sleep deprivation, trauma, or disease, the felt thickness of me changes, becoming jumpy, flattened, or porous. None of this means the self is fake. It means the self is engineered, evolved to integrate noisy channels into a stable enough platform for learning and cooperation, and its robustness comes from redundancy and arbitration rather than from a single throne. Practically, this view hands you tools to change habits. Don't appeal to a monolithic willpower. Nudge the systems that set thresholds. Train the attention networks that decide what enters the workspace, and restructure environments so the valuation systems don't have to fight uphill. to stabilize identity during upheaval, support the autobiographical builder, journals, photographs, and conversations provide external scaffolds that protect continuity when memory is overburdened, and protect the body map with routines that keep interoceptive signals regular. Meals, movement, breath, to soften unhelpful self-stories, target the narrator not with argument alone but with new experiences that let prediction errors revise the plot, acts of service that contradict "I am isolated," small mastered challenges that rewrite "I can't," social feedback from trusted others that retags faces and places with warmer meanings. And when you feel scattered, it can help to remember that conflict inside does not mean fraud. It means multiple subsystems with different mandates are each doing their jobs. One guarding comfort, one chasing growth, one maintaining social ties, one conserving energy. Your task is to convene them, not to erase all but one. The closing comfort is gentle and, I hope, grounding. You are not a single note, you are a chord sustained by many instruments. And on good days, the conductor's baton is just the agreement those instruments reach. Learn which sections you can cue with sleep, nutrition, breath, and attention. Strengthen the narrator with honest records. Give the valuation systems healthier rewards. And accept that sometimes the best you can do is retune rather than overpower. Seen this way, the self stops being a mystery to defend and becomes a craft to practice. Stitched. Yes, from competing processes, but stitched with intention, until the patchwork is warm enough to live in and strong enough to carry you forward. Animals read Earth's field with quantum tricks. You don't need a metal compass to find north if your body can turn light into a map. Many animals seem to do exactly that, reading Earth's magnetic field with chemistry that briefly borrows a page from quantum physics. And once you learn the outline, migration looks less like blind luck and more like exquisitely tuned sensing hidden in plain sight. The leading idea centers on special molecules called cryptochromes, light-sensitive proteins found in the eyes of birds, insects, and even some mammals, where a photon can kick off a reaction that creates a pair of unpaired electrons on neighboring parts of the molecule or on a partner molecule. And these electrons start their lives entangled as a unit with two possible joint spin configurations that chemists nickname singlet and triplet. Crucially, the tiny magnetic field of our planet, so gentle it barely tugs a paper clip, can still influence the rate at which these two configurations convert into one another, because the field shifts the energy landscape just enough to change how often the pair flips identity before the reaction ends. And those altered flip rates steer the chemical products down slightly different paths. If the reaction lives in the retina, where the products can modulate signaling to neurons, then the animal essentially gains a picture overlay that depends on magnetic direction. Turn your head, and the balance of reaction outcomes changes by a small but systematic amount, yielding a dim pattern in the visual field that marks the angle of the field lines relative to gravity and to the eye's geometry, an inclination compass rather than a bar magnet's north-south pointer, which fits what experimenters see in migratory birds that orient by the slope of the field, rather than by its polarity. Behavioral studies support this subtle picture with practical tests. European robins in simulated night skies choose the seasonally correct direction if the ambient light contains the right wavelengths to activate cryptochrome. Lose that ability under monochrome red light that fails to start the radical pair chemistry, and become confused when researchers add a weak, rapidly oscillating radio frequency field that specifically scrambles the spin flips, a disruption that makes little sense for iron crystals in the beak, but is exactly what a spin-dependent chemical compass would predict. The effect survives in noisy, warm conditions, the opposite of a quiet physics lab, which is part of the fascination. Biology seems to preserve just enough quantum coherence for just long enough, on the order of microseconds, to let the field tip the odds before the reaction products are read out by the cell, a triumph of molecular design in a messy environment. Cryptochromes are not identical across species, and their positioning in the retina matters too. Some studies have found patterns of expression that cluster in regions poised to deliver a directional overlay onto the normal visual stream, while others suggest multiple cryptochrome variants might contribute, one optimized for sensing at twilight, another for broader conditions. This does not rule out a second, iron-based magnetoreceptor elsewhere in the body. There is evidence for magnetite particles acting as torque sensors in the beaks of some birds or in the snouts of fish and turtles, but it neatly separates tasks. An iron sensor might tell you field strength or help with local gradients near landmarks, while the light-triggered radical pair in the eye provides a global heading tied to the tilt of Earth's field. The radical pair mechanism offers testable, quantitative hooks without drowning you in math. The contrast of the compass signal depends on the angle between the field and the molecular axes, on the time scale of the electron spin evolution relative to the chemical reaction, and on the presence of any environmental fields that would either scramble or sharpen the oscillations. That is why interference from human-made radio noise at specific frequencies can sometimes affect orientation in urban areas, and why careful shielding or field manipulation in the lab can turn a bird's internal compass on and off like a dimmer. Beyond birds, similar behaviors show up across the kingdom. Monarch butterflies maintain migratory headings with a light-dependent magnetosense. Fruit flies exhibit orientation shifts that vanish when cryptochrome is knocked out. Lobsters and sea turtles navigate long distances with a combined sense of magnetic inclination and intensity that marks latitude like an invisible gradient map. And even mole rats living underground respond behaviorally to field rotations despite scant access to light, suggesting that evolution had several tries at building magnetic sense, sometimes favoring chemistry, sometimes iron crystals, sometimes both. Skeptics used to worry that Earth's field is too weak to matter, but the trick is not brute force, it's resonance and timing. If the reaction pathway is designed so that yields are decided during the narrow window when spins talk to each other, then a field weak in absolute terms can still change the outcome enough for a nervous system to amplify downstream. The brain is very good at boosting small, consistent biases. Your eyes do it every day with faint contrasts at the edge of perception. And a compass overlay need not be bright to be useful. It only needs to be stable with respect to head and body orientation so that the animal can tie it to a star map, a polarized light pattern at dusk, or an internal clock. The educational punchline is practical. A magnetic sense does not give a complete route. It gives a reliable axis you can combine with other cues, smell, stars, coastline, learned landmarks, to build a robust migratory program that survives clouds, crosswinds, and partial information. As for open questions, they are delicious rather than embarrassing. How do neural circuits read and integrate the weak compass signal without confusing it with ordinary contrast? How do animals recalibrate when they move between regions with different magnetic inclinations, or when storms briefly distort the field? What genetic switches tune cryptochrome expression seasonally so that a non-migratory bird in summer becomes a steely navigator in autumn? And do mammals like dogs or bats lean more on iron-based sensors, while birds favor radical pairs, a division of labor that reflects different ecological needs? Each of these questions points to experiments already underway, from imaging retinal layers under controlled magnetic fields, to editing cryptochrome genes and watching orientation behavior change, to building cleaner countryside test sites where radio noise can be dialed like any other variable. Philosophically, the lesson is not that animals work magic, but that nature is shrewd with physics. If a planet offers a global, reliable signal, evolution will find a way to couple to it, even if the coupling requires keeping a whisper of quantum order alive inside a sunlit eye. For you, the gentle takeaway is twofold. First, migration is not a heroic guess, but a layered computation made by small bodies with big constraints. And second, the line between the quantum and the everyday is not a wall, but a seam that biology can stitch across when the payoff is high. The next time you watch a flock lift at dusk and fall into a shared direction as if pulled by a string, imagine a faint, rotating pattern painted over their visual field by photochemistry, an internal aurora tied to the planet's tilt, guiding them across oceans and continents without a map, only a compass that fits literally inside a molecule. And ask yourself what other quiet instruments life has hidden in plain sight that we have not yet learned to hear. Life may exploit quantum coherence. You can watch sunlight turn into order without wires or turbines if you look small enough. inside the green of a leaf, or the iridescence of an algal cell. Energy captured from a photon doesn't stumble randomly from molecule to molecule like a drunk in a crowd. It seems to travel partly as a coordinated wave that tests many routes at once, then settles on the best path to the reaction center where charge separation begins. And this wave-like efficiency is the heart of a quiet proposal in quantum biology that life, at least in some places, exploits coherence to move energy fast and with startling reliability. The stage is a light-harvesting antenna, a tidy cluster of pigments, chlorophylls, bacteriochlorophylls, carotenoids, held in precise geometries by a protein scaffold that isn't just a rack, but an acoustic environment with its own gentle vibrations. And when a photon is absorbed, the excitation that results is not confined to a single pigment, but spreads over several, becoming an excitant that can, for a brief window, behave like a delocalized object, sampling multiple pigments simultaneously. Ultra-fast laser experiments gave the first vivid hints. By hitting photosynthetic complexes with snapshots just a few femtoseconds apart, and reading the echoes with two-dimensional electronic spectroscopy, researchers found oscillatory signatures, beating patterns in the signals, that looked like the hallmark of coherent motion, as if the excitation was sloshing between pigments in step, rather than hopping in forgetful spurts. You'll find this story in bacteria that live in dim ponds, in the FMO complex that funnels energy to a reaction center with near-perfect fidelity, and in cryptophyte algae, whose antenna proteins work across different spectral bands, each case suggesting that the architecture is tuned to keep coherence alive, long enough to matter even at room temperature where thermal jostling is relentless. But the plot is more interesting than a simple "life is quantum" headline. Later studies showed that some of the observed beats can come from vibronic coupling, pigment vibrations coherently entangled with electronic states. So, what matters most is not pristine, isolated quantum waves, but a partnership between the excitation and the protein's motion, a kind of escorted travel, where soft vibrations in the scaffold shepherd the exciton through an energy landscape dotted with traps and detours. This is where a counterintuitive design principle appears. A little noise can help, and there is a just right amount of environmental bustle that actually boosts transport, a regime often called environment-assisted transport, because slight defacing prevents the excitation from getting stuck in local dead ends and keeps it surfing toward lower energy sites. Think of it like moving through a crowded market. Perfect order might trap you behind a slow walker. Pure chaos would make you lost. But a medium hum of motion opens gaps just when you need them. And the protein seems to keep that hum in tune by placing pigments at distances that balance coupling strength with the right spectrum of vibrations. The reaction center waits at the end of the funnel with a specialized pair of pigments ready to split charge in well under a trillionth of a second, and the whole assembly is arranged so that energy levels step downward in a gentle staircase, making backward travel unlikely. An energy funnel built not with wires but with chemistry and geometry. Plants don't sit still in their design either. Under different light conditions, many antenna systems can reconfigure, turning down coherence-aided funneling when the sun is harsh to protect themselves, or opening it up when light is scarce to capture more with less loss. Which means the very feature that looks like high science in a paper, tunable coherence, shows up as a real living trade-off between speed and safety. The debate isn't whether coherence exists, but how long and how usefully it survives. In warm, wet biology, coherence often fades within tens to hundreds of femtoseconds. Yet that is enough to steer the first steps. And once the excitation is headed the right way, classical hopping can finish the job. So nature seems to combine a quantum kickstart with robust handoffs. Different organisms exploit this blend differently. Purple bacteria with their neat rings, green sulfur bacteria with FMO acting as a wire-like bridge, cryptophytes with mixed pigment types that broaden capture, higher plants with stacked membranes that pack millions of complexes into thylakoids where coherence must coexist with crowding and dynamic regulation. The practical payoffs of understanding this aren't speculative fairy dust, they're engineering targets. If soft, structured disorder, plus brief coherence improves yield, then artificial light harvesters and organic solar cells might do better by mimicking these protein scaffolds, arranging synthetic pigments so their couplings and local vibrations sit in the same just right band, and manipulating the environment through solvents, polymer hosts, or nanoscale patterning, so that dephasing is not too little and not too much. Already, researchers building excitonic circuits in organic films or DNA scaffolded pigment networks report transport gains when they tune disorder deliberately, rather than pretending it can be eliminated. And device designers are learning to engineer noise the way an audio technician shapes background hiss to make a recording clearer. The caution you should carry is that coherence is not a cure-all. Some reported signals in early experiments were later reinterpreted, and not every photosynthetic organism needs or shows long-lived waves. Plenty succeed with beautifully optimized classical hopping once the antenna architecture is right. So the honest statement is that life uses whatever mix of quantum and classical tools works in context, and in certain antennas, coherence is part of that mix. What makes this story more than a lab curiosity is its ethical angle on complexity. The efficiency we admire arises not from eliminating mess, but from harnessing it. From matching delicate quantum tendencies to the rough rhythms of a protein. From letting short-lived waves make big decisions and letting slower, classical steps carry them out. If you want a mental image to keep, picture a tiny green city where pigments are buildings, protein vibrations are the patterned traffic, and a newly arrived quantum guest takes a quick aerial survey before choosing the boulevard most likely to deliver it to the center, then rides that boulevard with help from the city's hum. And when you step back into daylight, you can let the lesson travel with you. Sometimes speed and reliability don't come from bulldozing noise away, but from shaping it, from letting a fleeting coherence take the lead only as long as it helps, and from learning, like a leaf, to weave calm order out of sun and warmth and motion so that work begins in the right direction and ends in a charge you can use. A handful of rules. Make complexity bloom. Start with something small enough to miss if you blink. An ant leaves the nest, turns left at random, and when it stumbles on food, it walks home laying a thin ribbon of scent. And that ribbon nudges the next ant's choice of turn, which thickens the ribbon, which recruits another ant. And soon a highway forms from nothing but two rules. Follow stronger scent. Reinforce what you follow. Proof that rich order can bloom without a general or a map. Now widen the lens and you'll see the same logic in flocking birds and schooling fish, where each individual obeys simple priorities. Keep a comfortable distance. Match your neighbor's speed. Steer toward the group's center. And those modest cues tame chaos into a coordinated ballet that splits around obstacles and recombines. Not because any one bird knows the choreography, but because local corrections propagate into a global pattern. Slime molds solve mazes by making and breaking tubes that carry nutrients more efficiently, reinforcing good paths and retracting bad ones with no blueprint except grow where flow is. Easy. And colonies of bacteria switch between free swimming and stationary states via chemical quorum rules that say, act, together when enough of us are nearby. Building biofilms whose strength emerges from countless yes-no flips. The same many small votes. One large outcome turns up in materials. Add just enough links to a scattered network and suddenly a system-spanning path appears, a percolation threshold that marks a phase change from isolated islands to a connected continent, and that is why forest fires, disease outbreaks, and even ideas on social platforms can smolder for ages, then roar across a landscape when the web of contacts crosses a critical density. You can watch Emergence in a computer with a game that has only a handful of pixel rules. Cells live or die depending on their neighbors. And out of that simplicity, tumble gliders, clocks, even logic devices, reminding you that complexity doesn't require complicated ingredients, only the right interactions. Morphogenesis, how an embryo paints stripes or spots, can be sketched by two chemicals that diffuse at different speeds and encourage or inhibit each other, and those reaction diffusion rules, written once, generate the leopard's coat, the angelfish's lattice, and the spiral swirl of a seashell. Economics layers human intention atop simple exchange. Prices float not because any one person computes the market's value, but because local trades push the number until supply and demand balance. And yet the same emergent order that makes grocery aisles full can also kindle bubbles when feedback loops become reflexive, expectations feeding prices feeding expectations. An example of how self-organization can be robust and fragile at once. Cities grow by accretion and preference. People cluster near jobs. Streets follow desire lines. Businesses sprout where foot traffic thickens. And soon you get scaling laws. As population doubles, measures of innovation, wages, and even infrastructure follow predictable curves that urbanists can use to plan transit or energy. Another sign that macro regularities can be read off from micro decisions. Inside your skull, emergence takes on its most intimate meaning. Neurons obey local rules of excitation and inhibition. Plastic connections strengthen with use and weaken with neglect. And out of those interactions rises something no single neuron contains. A moving workspace of attention, a sense of continuity, language that flexes with context, and the possibility of insight that feels like it came from nowhere, because the somewhere was a network reorganizing beneath awareness. Artificial systems borrow the recipe. A neural network with simple units and a learning rule can recognize faces or transcribe speech once trained on enough examples, not because any unit knows what a face is, but because layers of local filters compose into features and features into categories. And if you probe the network, you'll find motifs like edge detectors and texture analyzers, tiny specialists whose cooperation yields general skill. Traffic engineers tinker with emergent jams by adjusting rules at ramps and lights, metering rates, variable speed signs, zipper merging, small interventions that change local incentives and dissolve global standstills. And energy grid operators keep blackouts at bay by smoothing local loads so that cascading failures never find a footing. What unites these examples is not mysticism, but architecture. Feedback, positive to amplify promising paths, negative to damp runaway loops. Locality, each agent uses nearby or recent information. And adaptation, rules that learn from outcomes. And when those pieces are tuned near the edge of order and disorder, where a small nudge can propagate but not explode, systems become both responsive and stable. You can hear critics say that calling something emergent is hand-waving unless you can predict it, so it helps to remember that emergence is a program for explanation. Identify the micro rules, simulate or analyze how they interact, and show that the macro pattern follows, an approach that has matured into fields like agent-based modeling and network science. Sometimes the leap from rules to pattern passes through universality, the discovery that wildly different systems share the same large-scale behavior near critical points, which is why a magnet just above its ordering temperature and a market at the edge of a crash can exhibit similar fluctuations and power law tails in the sizes of their clusters or moves. The philosopher in you might ask whether describing a mind as emergent from neurons reduces meaning to mechanics. But the more generous view is that emergence lets layers keep their dignity. Chemistry explains biology's machinery without erasing organisms. Cognition explains behavior without erasing meaning, and each layer can be lawful in its own vocabulary while remaining connected to the ones beneath. The practical upshot is design wisdom you can use. If you want a team, a classroom, or a platform to self-organize well, set clear micro rules, reward helpful contributions, make feedback immediate, cap local loads, publish simple heuristics for conflict, and then watch for unwanted loops that need negative feedback or friction to stabilize. In robotics, swarms of cheap bots obey avoid collisions, match heading, explore when signals are weak, exploit when signals are strong, and collectively map caves or assemble structures without a central commander. Resilient because losing a few units doesn't kill the whole. In public health, local reminders and small conveniences nudge individual choices that add up to herd effects, while network-aware strategies target bridges between communities to stop spread at lower cost. Even personal habits can be framed emergently. Don't hunt for a single act of willpower. Adjust your micro rules. What's visible on your desk, the default option in your apps, the small rewards attached to repeated acts, and let the macro pattern grow from repeated local wins. If you want a litmus test for when emergence will help, ask 3 questions. Are agents limited to partial information? Do their actions change the information for others? And is there feedback that can stabilize successes and extinguish failures? If yes, you're in a landscape where small rules can write large stories. The caution is simple but firm. Emergence is not a free pass to ignore accountability. Who sets the rules matters, and the system did it, can hide avoidable harm. So ethical design demands transparency about incentives and escape hatches when patterns turn perverse. Keep one image to close. Pour a handful of iron filings near a magnet, and lines of force appear as if sketched by an invisible hand. Yet no filing knows the picture. Each turns to its tiny rule, and the drawing emerges. Likewise, on a winter sidewalk, 100 footsteps carve a diagonal desire path across the snow, not because a planner traced it, but because each walker shaved a step off their journey and the path remembered. Your world is full of these quiet drawings: ant highways, zebra stripes, power grids, languages, neighborhoods, and thoughts. And once you learn to see them, you inherit a craft. Tune a few rules with care, supply the right feedback, give the system room to learn, and complexity will often meet you halfway, blossoming into forms that are richer than any one mind could have designed alone. You can push a sail with light. You can move a craft with nothing but sunlight if you give light something wide and obedient to push against. Photons carry momentum, even though they have no mass. And when they arrive, they tap a sail with a force so gentle you can't feel it, yet so steady that over days and weeks it adds up to real speed. The way a river shapes rock, not with a blow but with patience. Begin with the simple physics you can keep in your pocket. At Earth's distance from the sun, each square meter of sunlight delivers about a kilowatt of power, and the associated pressure is tiny, only a few millionths of a pascal for an absorbing surface, and roughly twice that for a perfect mirror. But multiply that by a sail the size of a tennis court, and you get tens to hundreds of micronewtons of continuous shove, which for a craft built light enough becomes a quiet acceleration you can aim. Reflection matters because reversing a photon's direction doubles the momentum change. So real sails use ultra-thin, mirror-bright films of aluminized plastic stretched on booms, promoting reflectivity and slashing mass until the sunlight to kilogram ratio finally favors motion. You don't steer by pivoting a mast into a wind. There is no wind, so attitude control is its own art. You trim the sail's angle to the sun so that the component of push that helps your orbit grows, while the component that fights it shrinks. You twist corners with tiny tip vanes or reaction wheels so the pressure itself helps you hold the new pose. And because the sail is both engine and rudder, every gentle change in pitch or yaw writes directly into your path. The trick sounds delicate, but space has already proved it. Thin films have unfurled like silver flowers and shown that, once deployed, they can climb their orbits by sipping sunlight, raising apogee pass by pass without burning a gram of propellant, a rehearsal for missions that will one day loiter over poles, hover displaced from traditional Lagrange points, or spiral outward patiently toward the outer system, using nothing but starlight. Understanding why this is legal under the same rules that cap speed also sharpens your intuition. The speed limit in relativity restricts how fast a signal or object can move through space, not whether a steady sub-millimeter per second push can accumulate over months into kilometers per second of velocity. Sails are slow starters, but unbeaten at endurance, turning continuous power into cumulative dV, the way an efficient engine turns fuel into range. Sunlight's pressure doesn't just move our inventions, it also sculpts the small things we didn't design. The dust tail of a comet points away from the sun, in part because radiation pressure sweeps tiny grains outward, while an allied effect called Poynting-Robertson drag very slowly drains orbital energy from particles as they absorb sunlight and re-emit it, making them spiral inward toward the sun. A double reminder that light writes on matter even when no one is watching. At smaller scales still, lasers pinch and hold microscopic beads with optical tweezers, not by heating them into compliance, but by using intensity gradients to tug on the bead's induced dipole. a laboratory sibling of sail pressure that turns photon momentum into a tool for biology and soft matter physics. Caveat myths are worth clearing here because they teach good habits of mind. The toy Crookes radiometer spins in sunlight not because photons push harder on dark veins than on bright ones, but because residual gas warms on the dark side and flows around edges to produce a thermal creep. If you pump the bulb hard enough or shine a strong laser, the direction flips and the radiometer finally obeys radiation pressure. An elegant reminder that experiments must separate multiple causes. Back in space, engineers extend the basic concept by driving sails with light we make. A ground or orbital laser array can, in principle, hurl a wafer-scale sail to a fraction of light speed by pouring many megawatts into a tiny target, turning terrestrial infrastructure into a launch pad for star-chasing chips. Here, materials science becomes the gatekeeper. Ultra-thin photonic films must reflect without absorbing to avoid cooking, remain stable under gigapascal-level light stresses, and survive relentless acceleration without wrinkling into failure. And beam control becomes an art of diffraction, phasing, and atmospheric compensation if the array lives on Earth. For near-term duties, sunlight alone is enough to matter. A square sail tens of meters across on a spacecraft, the mass of a suitcase, can trim orbits, study asteroids without carrying a tank of propellant, or rendezvous with interplanetary targets on a budget of patience rather than fuel. And because the propellant is free and everywhere, mission lifetimes are bounded more by materials fatigue and electronics than by mass flow. If you want to feel the numbers rather than memorize them, picture this: a perfectly reflecting 1 square meter patch at Earth's orbit feels a push of roughly 9 micronewtons, about the weight of a grain of sand. So 100 square meter sail totals about a millinewton. Mount that on a craft of a few kilograms, and you are in the realm of tens of micro-Gs of acceleration, only centimeters per second per minute. But keep that up for a day, and you've added meters per second. For a month, you've added hundreds. And for a year, your trajectory is something ordinary rockets would need tanks to match. The art is choosing when to tack relative to your orbital motion. Facing the sun square on pushes you outward and slows your orbital speed. Good for climbing. Tilting forward can add energy along track. Good for raising perigee. And combinations of these trims let mission designers write geometric recipes for where to be and when, without a single thruster firing. Sunlight's shove also shows up as noise in exquisitely sensitive detectors, gravitational wave, observatories, and drag-free. Satellites work hard to cancel it with balancing, thrust, or clever shielding, proof that photon pressure is not an abstract textbook term, but a practical force you either use or must mitigate. If you prefer the romantic image, keep it, because the science doesn't spoil it. A sail is exactly what it sounds like. A sheet capturing the faintest of winds, except the wind is a rain of quanta and the ocean is the vacuum. And if you're tempted to think a technology so gentle must be fragile, remember that gentleness is the point. By swapping explosive impulses for a permanent, directional whisper, you gain a tool that rewards patience with reach, that trades fuel for film, and that replaces plume contamination and bang-bang control with the elegance of geometry. The deeper lesson lies beyond spaceflight. Nature gives you many situations where small, steady influences dominate over long times. The secular tug of light on dust, the daily pressure that shapes a pendulum's equilibrium in a sunlit room, the measurable push of laser light on mirrors that precision experiments must count. So learning to see photon momentum isn't just learning to launch sails. It's learning to respect the cumulative power of the barely felt. Imagine finally, standing in a clean room and watching a sail bloom from a canister like a square sunrise, edges pulled taut, film glittering with reflected LEDs. Then picture that same square months later, the Earth now a coin in the distance, the sail quietly canted against the sun so that every photon gives up a sliver of its motion to the journey. No fumes, no burn, only light becoming movement and patience becoming distance. There are more chess games than atoms. You think a board with 64 squares and a handful of wooden pieces should be a small world, but open the lid and you fall into an ocean. From the quiet starting line, Each modest move branches into more possibilities. Those branch again, and after only a few turns, the number of distinct games balloons beyond anything your intuition can hold. So large that even if you compared it to the estimated count of atoms in the observable universe, the game tree would still dwarf it, a fact first sketched by Claude Shannon when he argued that there are around 10 to the 120th different chess games, a combinatorial sky that makes the universe's roughly 10 to the 80th atoms look almost provincial. This isn't magic, it's arithmetic meeting rules. At the start, there are only 20 legal moves, but the average branching factor quickly rises into the dozens, and a 40-move game with that much freedom mushrooms into a count that grows like a wildfire. Multiply choice by choice by choice, and you reach numbers that the human tongue can't comfortably say. Legal positions alone, states you can actually reach following the rules. With check and castling rights respected, pawns where pawns can be already number in the tens of quadrillions or more. And that's before you tie them into sequences that avoid loops under the repetition and 50-move rules. The lesson isn't that chess is infinite. It's that finiteness can still be functionally unsearchable because so much bigger than your lifetime and infinite are indistinguishable in practice. Computers survive the sea by refusing to drink it all. Early engines learned alpha-beta pruning, which throws away branches that cannot possibly beat a known line. Transposition tables. Remember that different move orders can land on the same position and avoid re-evaluating what's already known. Opening books compress centuries of human exploration into guided first steps. Endgame table bases turn the final handful of pieces into solved landscapes where perfect play is literally pre-computed. Modern neural engines don't just count. They learn to guess which positions smell promising, letting them leap toward value rather than slog. But even with all that, nobody knows chess in the sense of having mapped the whole galaxy of games. What we have are islands of certainty and wide oceans of maybes, which is why a new novelty on Move 12 can still surprise grandmasters and strong engines alike. And if you think this is a quirk of a board game, look around. The same explosion haunts many ordinary problems. How many distinct ways can a bundle of proteins fold before one shape locks into function? How many logistics routes can a delivery network try before fuel and time say stop? How many sensible paragraphs can you assemble from a vocabulary before you drown in the space of word orders? How many product options does a shopper face once color, size, and feature are multiplied together? The moral is not despair but design. We manage huge spaces by exploiting structure, symmetry, and constraint, by noticing that many choices are effectively the same under a relabeling, by carving the search down with heuristics that are good enough, by chunking patterns so a mess of details becomes a single graspable shape. Human players do this intuitively. Recognizing a pawn chain or a weak square is a compression trick, a way to name a substructure and carry it whole. And a beautiful combination is less a blind stumble through possibilities than a narrow corridor hewn by understanding. Chess also teaches humility about forecasting. Because the space is so large, evaluation is always local and provisional, and the best plans are the ones that keep many futures alive. A strategic version of robust decision-making that works in investing, policy, and career choices as well. There's another softer lesson. Abundance does not guarantee meaning. There are more legal games than we could ever play, but only a sliver will be memorable. A truth that travels easily to art, science, and life, where the count of available moves always exceeds the count of worthwhile ones. It's comforting too to recognize that limits create beauty. The knight's L, the bishop's diagonals, the tethered forwardness of pawns. These constraints prune the combinatorial tree just enough that human taste can find pathways of clarity, which is why elegant endgames and crisp sacrifices stand out like constellations in a crowded sky. And if you need one more reason to care, consider that combinatorial blow-up is a frontier we navigate every day when algorithms recommend movies, route ambulances, or schedule power grids. Each system survives by noticing structure and discarding most of the tree early. In that light, the phrase "more chess games than atoms" stops being a party trick and becomes a practical intuition pump. When a space of options grows multiplicatively, raw enumeration fails. Only strategies that learn, compress, and steer by value can cope. So the next time you nudge a pawn 2 squares and feel the quiet of the pieces, remember what's hiding behind the silence. A vast, branching forest of futures that no mind or machine will ever finish listing. And yet a small set of principles: control the center, coordinate your forces, protect your king, respect your opponent's threats, can guide you through that wilderness toward moments of crisp inevitability, where a complicated world briefly reveals a simple truth and the right move, among astronomically many, feels suddenly unmistakably clear. Matter is mostly empty, but never empty. You've been told that matter is mostly empty, and that sounds like a confession of hollowness. But the more accurate and far more interesting truth is that what feels like emptiness is a spacious stage filled edge to edge by fields, and what we call particles are specific ripples or lumps on that stage. So when you press your palm against a table, you aren't meeting solid billiard balls packed tightly together. You're encountering organized excitations of the electron and electromagnetic fields that refuse to overlap beyond certain limits and push back with exquisite reliability. Begin with scale, because it gives your intuition something to hold. If an atom were the size of a cathedral, its nucleus would be a marble near the altar, and the electron cloud would fill the nave as a mist, whose density is highest near the center and thins outward. Not a swarm of tiny planets, but a probability distribution describing where the electron field is most likely to show itself. The fact that most of that volume is not densely occupied doesn't mean nothing is there. It means that the fields that define chemical bonds, optical colors, and electric currents extend through that space even when no individual particle happens to be detected at a particular point. Push a bit deeper and the familiar notion of hardness reshapes. 2 atoms rarely let their electron clouds interpenetrate freely because the antisocial rule for electrons, no 2 can occupy the same quantum condition, forces them into distinct patterns. And that exclusion, together with electromagnetic repulsion between like charges, produces the stiffness you feel as solid. The chair resists your weight, not because tiny bricks buttress one another, but because the energy cost of compressing overlapping electron states and bending the lattice's shared fields rises sharply, and your muscles, through your hand, negotiate with that cost. History showed this in an earthy way. Early scattering experiments flung charged projectiles at thin metal foils and found that most sailed through vast atomic volumes undeflected, while a few rebounded violently from compact, positively charged cores, evidence of space within matter, yet any builder knows a steel beam can hold a roof because the arrangement of atoms and the rules of their fields make collective resistance that vastly exceeds the mass packed into nuclei. The particles are excitations line becomes more than a slogan when you meet it piece by piece. There is an electron field permeating all of space. When enough energy and the right conditions concentrate, a localized, stable bump in that field behaves as an electron with the same charge and mass wherever you find it. The photon is an excitation of the electromagnetic field, able to propagate freely. Quarks and gluons are excitations of still other fields, confined by their own rules into protons and neutrons. And most of the mass of those protons and neutrons isn't the sum of their quarks' mass, but the stored energy of their churning fields, trapped by the strong interaction in a compact volume. So stuff is less a pile and more a budget of energies lodged in organized motion and binding. Once you're comfortable with the idea that fields fill space, a famous twist stops being esoteric. One field, the Higgs field, has settled into a non-zero value everywhere, even in the quietest conditions, and particles that couple to it acquire inertia from that steady background. It isn't that the Higgs sprinkles mass onto things like seasoning, it's that moving certain excitations through a medium with this built-in value resists acceleration, which we measure as mass, a mechanism that ties the idea of empty space to the very weight you feel in your legs. The same logic plays at humbler scales. In a magnetized material, you can talk about spin waves and domain walls as excitations of a collective field of aligned moments. In a crystal, vibrations of the lattice, phonons, carry heat and sound. In a superconductor, pairs of electrons form a collective state whose field excludes magnetic flux from the bulk and lets current flow without resistance. None of these quasi-particles is a little marble hidden in the material. The material itself, through its fields, supports patterns that move and interact as if they were particles. And engineers use those patterns to design sensors, memories, lasers, and more. If you want to test your grasp of mostly empty but never empty, look at light and transparency. A pane of clean glass is mostly atomic spacing when judged by volume, yet it steers light with precision because the electromagnetic field of the light couples to the electron field in the material, polarizing it briefly as the wave passes, so that the combined fields propagate at a different effective speed. The glass bends and delays light not by interposing dense pellets, but by offering a medium whose fields respond in step. Even color is a field story. The allowed excitations in a molecule, its energy levels, decide which wavelengths are absorbed and which pass. So the red of a berry or the blue of the sky is less about pigments stuck in a place, and more about how fields with specific energies are permitted or forbidden to oscillate there. The space around and within you isn't inert between these events. It's a meeting ground where interacting fields establish what can happen when. Whether a bond forms, a current flows, or a photon passes. This view also clarifies common puzzles. If matter is mostly empty, why can't you walk through walls? Because empty does not mean available. And the arrangements of the chair's fields and your body's fields create boundary conditions that forbid that overlap without enormous energy. Why do atoms keep their size? Because if electrons tried to collapse onto nuclei, their wave-like nature would squeeze into a smaller and smaller region, raising their kinetic energy and pushing back against confinement until a stable size emerges from the tug-of-war. A balance written into the field's equations. Why does a vacuum chamber still affect how atoms and light behave? Because vacuum means no real particles present, not no fields. And the permitted modes of those fields depend on boundaries, materials, and motion, which is why precision instruments treat even the surrounding emptiness as a component to be designed. This perspective is not a philosopher's luxury. It's practical literacy for modern technology. Transistors work by sculpting electron fields in silicon channels, with gates that raise and lower the energy landscape. LEDs and lasers coax electron and hole excitations to recombine in ways that release photons into favored modes. MRI scanners read the collective precession of nuclear spins, again field excitations inside your tissues, and particle colliders don't throw little rocks so much as they inject energy into fields and read the signatures of the excitations that briefly appear. Even gravity, which we feel as the weight of things, can be described geometrically rather than as a force between marbles. Mass and energy tell spacetime how to curve, and curved spacetime tells excitations how to move. A shift in mental framing that turns the misleading question, "What is space made of?" into the better question, "What are the rules that fields obey here?" If this sounds abstract, let it be grounding instead. The coffee cup on your desk, your skin, the air, the sun's light, each is real precisely because fields are real, filling every region so thoroughly that changing their patterns changes the world. You can't scoop a handful of field the way you'd scoop sand, but you can pump, shape, and store excitations. And that is what communication, computation, and measurement do all day. And there is a gentle philosophical payoff, too. Mostly empty often tempts people toward existential thinness, as if sparsity meant insignificance. But in physics, the room is left on purpose. It gives fields space to express structure, lets delicate patterns stand out without constant collision, and allows a handful of simple principles to scale into the riot of materials, organisms, and experiences you know. So the next time you tap a tabletop, imagine not a packed wall, but a disciplined crowd of field configurations holding their ground, and recognize that the quiet between nuclei is not a void but a canvas already primed, everywhere, always, on which the excitations we call particles draw the world you can touch, see, and be. Your brain can see a single photon. You don't need a flood of light to see, Your night vision is built to make decisions at the edge of silence, and in deep darkness your eyes and brain can register the arrival of a single photon, a grain of light so small that counting it feels like eavesdropping on the universe. The feat begins in the outermost layer of the retina, where rod photoreceptors pack their discs with rhodopsin, a pigment whose shape can flip when it absorbs a photon. And this microscopic twist kicks off a chemical cascade that amplifies the event until an electrical signal large enough to notice reaches the next cells in line. One activated rhodopsin can shut many ion channels in its host rod for a brief moment, changing the cell's current by a measurable amount, so the system converts a molecular nudge into a macroscopic whisper. Amplification is the trick that lets single quanta leave footprints. But being able to respond to one photon is not the same as reliably seeing it, because the night is full of imposters. Even at body temperature, a few rhodopsins spontaneously flip shape without any light, a dark noise that produces false alarms, and other cellular fluctuations add their own jitter. So the retina and the brain must walk a statistical tightrope. Set the threshold too high and you miss real photons. Too low and you start believing noise. Evolution's compromise is elegant. Many rods converge onto a single downstream neuron in the scotopic, low-light pathway, pooling evidence across a neighborhood of detectors while retaining just enough independence to veto outliers. And those downstream circuits, which include specialized bipolar and amacrine cells, shape the signal before it reaches ganglion cells that send spikes to the brain. Psychophysics experiments that deliver carefully timed, greatly dimmed flashes show that human observers can detect light when only a handful of photons land on the cornea, and with modern single photon sources, the tests can go further. When trials are designed so that, on average, 0 or 1 photon arrives, people still perform above chance at reporting which interval contained the light, a result that sits beautifully with rod physiology and the statistics of rare events. Your pupils contribute by widening in darkness to admit more light, and your rods grow more sensitive after minutes without bright exposure. A slow biochemical tuning called dark adaptation that replenishes pigments and rebalances circuits so that the same tiny currents carry more weight. Because rods feed into a system that values any change at all over fine detail, the image you get near the threshold is grainy and monochrome. Color vision is a cone specialty that needs many more photons per pixel. But even without color, the brain does smart things with faint signals. It integrates across brief windows, in time to boost the odds that a real photon's consequence rises above fluctuation, and it compares neighboring regions so that tiny differences stand out. A form of local contrast enhancement that makes a dim star pop when you look slightly to the side. There is art in the behavior that supports this biology. Astronomers learn to avert their gaze to engage the rod-rich periphery and to breathe slowly so that small vascular pulsations don't masquerade as twinkle. And hikers notice that after an hour by the campfire, they can suddenly trace the Milky Way once they step into the trees and let their chemistry catch up. At the level of quantum limits, the whole visual apparatus has to live with shot noise, the graininess that comes from light arriving in discrete packets with random timing. So no matter how perfect the optics or how clever the circuitry, there is a flaw to how certain you can be about something versus nothing in very dim conditions. Intriguingly, single rods are not only sensitive, they are stable. The waveform produced by one photon looks nearly identical from trial to trial in a given cell, which helps downstream neurons separate real photon shape from messier background flicker, and the retina further reduces noise by wiring rods through a dedicated pathway that filters for the characteristic timing of genuine single photon events. The brain's contribution goes beyond being a passive receiver. Higher areas weigh context and expectation, which can shift your criterion for saying, "I saw it," a subtlety that signal detection theory captures when distinguishing sensitivity from bias, and experiments that reward accurate no responses as much as yes show that people can tune how cautious they are without changing the underlying sensitivity of their rods. The ecology of your nocturnal experience has other quiet rules. As the world darkens, the brightness at which colors vanish slides toward blue, a Purkinje shift that reflects how rod and cone sensitivities trade off across wavelengths. The night sky itself helps by delivering photons without glare, which is why even very small telescopes unlock more stars. The optics simply concentrate sparse photons onto fewer rods. More than a party trick, single photon vision is a design principle with spin-offs. Artificial detectors mimic rod amplification to see weak fluorescence in biology labs. Machine vision systems borrow retinal strategies for pooling and thresholding sparse data. And clinical tests that present barely their flashes can diagnose early retinal disease long before gross visual acuity fails, because ailing rods lose their exquisite low-light performance first. Awareness of the limits can make you kinder to your senses. When a friend claims they saw a flicker at the edge of vision, they might be operating at the same statistical boundary where you would have said no, and both reports can be honest. And understanding the strengths can make you braver in the dark. Your eyes are better instruments than you think once you give them time and quiet. Turn down bright screens before stepping outside. Keep one eye closed if you must glance at a light, and let minutes, not seconds, pass before judging what you can and cannot see. If there is a larger reflection to take home, it is that your body was built to hear the smallest whispers of the physical world. A single photon can bend a rod's chemistry. Single molecules can excite olfactory receptors. Single hair cell deflections can announce a faint sound. In each case, evolution has wrapped amplification around quantum-limited events and then added filtering and consensus, so that noise does not drown meaning. Sight at the one photon level is not supernatural. It is ordinary physiology run to its limit, and the comfort in that knowledge is simple. You are already equipped to meet the night with instruments tuned to rarity, to let your eyes steady themselves until stars you thought weren't there condense into points, and to recognize that perception is not a blunt floodgate, but a careful counter that can, when you ask it gently enough, register the fall of a single grain of light. Maps are not the territory, especially in physics. You can draw a coastline with a thick marker, a fine pen, or a satellite's laser, and each picture will look true from arm's length. Yet if you walk the shore, you discover that every map is a choice about what to keep and what to ignore, and physics is built from the same kind of choices. A model is not the world. It is a disciplined sketch that predicts parts of the world under stated conditions. And the art is knowing both its power and its borders. Take gravity as a friendly starting point. Newton's inverse square law is a superb map for tossed balls, satellites, and tides, so good that we still use it to steer probes, but it breaks in strong fields and at high speeds, where Einstein's curved space-time map predicts the extra precession of Mercury and the time dilation that GPS must correct to keep your phone honest. And yet even Einstein's map is not the land, since we stitch quantum fields to it awkwardly and watch black holes raise questions about information that our equations can't settle. Move to gases and you meet the ideal gas law, a clean plane in the space of pressure, volume, and temperature that works until molecules start talking to each other strongly, at which point van der Waals terms or full statistical mechanics revise the sketch. And if you keep pressing the system toward a critical point, you discover that many materials share the same large-scale behavior regardless of microscopic details. Universality, a reminder that different territories can be navigated by the same contour lines when viewed from the right height. History keeps us humble about predictive maps that misplace the mountain. Neptune was a triumph of perturbation theory. There must be a planet here, worked. But the Mercury anomaly was not solved by a hypothetical planet Vulcan. It required a new geometry, and Ptolemy's epicycles, despite being good at fitting old observations, mistook curve fitting for understanding. This is why physicists demand more than accuracy on last year's data. They want constraints, counterfactuals, error bars, and reasons to expect success outside the training set, because a model that cannot say where it will fail is a superstition wearing numbers. Many of our best tools are openly effective, meaning they are guaranteed, only within a regime. The standard model makes glorious predictions for collider experiments while acknowledging gravity offstage. Nuclear physics uses potentials that summarize fierce substructure. Fluid dynamics treats water as a continuous medium, even though it is molecules all the way down. And band theory explains solids by pretending electrons move in gentle periodic backgrounds, then yields to new maps, quasi-particles, topological invariants, when materials surprise us. None of this is a confession of weakness, it is a strategy. You write a model at the scale relevant to your questions, embed the assumptions in the equations, linearity, homogeneity, equilibrium, calibrate its parameters against careful measurements, and then respect the domain where those assumptions hold. Even the axes can be a choice rather than a fact. Coordinates, gauges, and unit systems are conveniences, not essences. So two physicists can tell the same story in wildly different symbols and still agree on what detectors will click. And Noether taught us that the deepest features of the territory are often symmetries whose shadows are conserved quantities. But choosing a gauge or a frame does not conjure a new reality, it just tidies the map. The wave function in quantum theory dramatizes the point. Whether you treat it as a catalogue of betting odds or as a physical field, its role in prediction is clear. You compute amplitudes, square them to get chances, and test those chances with statistics. And different interpretations sketch different metaphysical landscapes without changing the distribution of clicks on a screen. In cosmology, we read the sky through models so large no human can visualize them whole. Dark matter and dark energy are not decorations. They are placeholders for consistent ingredients that make the map match lensing, clustering, and the microwave background. And if future observations force us to redraw the legend with modified gravity or new particles, we'll do so for the same reason cartographers rename rivers, because reality pushed back. Simulations extend the metaphor further. A climate model is not a planet. It is a hierarchy of coupled equations that translate energy balance and fluid motion into trends and variability and verification. Did we solve the equations right? Is different from validation. Are these the equations nature uses at this scale? A good simulation earns trust by reproducing out-of-sample patterns, by getting multiple lines of evidence to agree, by quantifying uncertainty from both parameters and structural choices, and by failing gracefully in known edge cases. Chaos tightens the screws. Weather is sensitive to initial conditions, so to forecast responsibly, we run ensembles and report probability cones rather than single, confident tracks, just as a particle physics fit quotes confidence intervals, not magical exactitudes. All models are wrong, some are useful, is not cynicism, but housekeeping. It reminds you to write down assumptions, to publish residuals along with glossy plots, and to prefer simpler maps when two explain the data equally well. Occam is not a law, but his razor prevents you from mistaking ornament for insight. Instruments deserve a paragraph of their own because you never observe the territory raw. You observe through a device whose transfer function is itself a model. Telescopes have point spread functions, detectors have dark counts, spectrometers have line-shaped distortions, and careful physics inverts these effects with calibration stars, reference lamps, and blanks. Every claimed anomaly lives or dies by whether you modeled your instrument as well as you modeled the universe. The habit that protects you from reifying your map is to keep a ledger of regimes and failure modes. Newton for speeds much less than light and weak fields. geometric optics when wavelengths are tiny compared, to apertures. Ideal, MHD, when plasmas are collisional and scales are large. Poisson statistics when counts are low. Gaussians only when central limit conditions apply. And to carry a kit of translation tricks across maps. Dimensional analysis, to sanity check formulas. Non-dimensional numbers, Reynolds, Mach, Knudsen, to place yourself on the chart, back of the envelope estimates, to sniff out nonsense before it wastes a week. There is a moral payoff here you can use outside labs, in policy, medicine, and finance. We often mistake a calibrated dashboard for the world itself, then blame reality for disobedience when the dashboard was never designed for the new regime. The cure is the same as in physics. State assumptions, test predictions where it hurts, update when the residuals talk, and resist the warm glow of a model that flatters your priors. None of this should drain the romance from discovery. If anything, it adds a wiser awe. Models are how finite minds touch a vast, layered world, each one a lantern that lights a region without claiming to be the sun, and progress is the practice of carrying more than one lantern, learning where each throws clean light, where shadows creep in, and how to stitch their beams into a map good enough to navigate by, while keeping a pilgrim's humility that the terrain, when you reach it, may still turn your paper sideways and teach you something new. The universe may not have an edge or a center. Stand in a field on a clear night and try to point at the universe's center. You will end up pointing at yourself, not out of vanity, but because expansion makes every quiet vantage feel central. And the deeper lesson is that the cosmos, as best we can tell, may have neither a physical edge you could fly past, nor a preferred middle that other places revolve around. The key is to separate what you can see from what the whole may be, and to trade the picture of a fireball exploding into empty space for a calmer one, in which space itself stretches everywhere at once, carrying galaxies along so that from each galaxy's perspective, the others recede, faster if they're farther, in a pattern that does not privilege any throne. This is not hand-waving, but a disciplined simplification backed by observation. On large scales, much larger than clusters and filaments, the distribution of galaxies looks uniform, and the light left over from the early universe. The microwave afterglow arrives nearly the same from all directions after you account for our own small motion, a twin testimony that, at grand scales, the cosmos is statistically the same wherever you stand and whichever way you look. Once you grant that homogeneity and isotropy, the math of expansion gives you a gift that diffuses the center question. If the scale of the cosmic grid grows with time, then any two moving points see their distance increase in proportion to how far apart they already are. And that proportional growth, projected backward, brings everything closer together without selecting a special origin in today's space. A balloon with dots on its surface is often used to prime the intuition. Inflate it and each dot sees the others recede while there's no dot singled out as the start, but the balloon is only a sketch because the real universe need not be curved like that surface nor embedded in a larger room. A loaf of raisin bread rising is another metaphor. The raisins drift apart as the dough swells, yet no raisin owns the center of the loaf, and there is no crust across on the inside, just more bread. If your next reflex is to ask, then where did the expansion begin? The honest answer is that the beginning, if there was one, is a boundary in time, not a location in space. When we track light back far enough, we reach a hot, dense phase where atoms could not yet hold together. And earlier still, our current physics goes silent. But nowhere in that story does a center point through which everything burst appear. Instead, distances shrink everywhere as you follow the clock back. And the phrase Big Bang describes a time when the whole observable patch was compressed and hot, not an explosion into pre-existing emptiness. Edges, too, recede once the picture is straight. The part we can observe is bounded by the distance light has had time to travel since the fog of the early universe cleared. So there is an edge to our observations, a horizon that marks how far our past light cone reaches given the entire expansion history. But that boundary is not a wall in space. It's a limit in time and information, and beyond it the cosmos could continue in whatever topology the laws permit. Even the shape of space, flat, positively curved like a sphere, or negatively curved like a saddle, does not settle the edge question in the way everyday geometry would tempt you to think. A positively curved space can be finite, yet unbounded, like the surface of a sphere that lets you roam forever without finding an edge. And a flat or negatively curved space can be infinite without any center. Stranger topologies are also allowed by the rules, like a three-dimensional analog of a wraparound game map, where going far enough in one direction returns you to your starting point from the other side, a cosmic hall of mirrors that is still centerless and edgeless in the meaningful sense. Measurements today hint that on the scales we can test, space is very close to flat, and the microwave background is extraordinarily smooth after we remove our small local drift, which is why the working picture keeps the large-scale map simple. No special hub, no outer rim, just a geometry that, when evolved forward from early conditions, yields the structures we see. This perspective also cures common confusions. When people say galaxies speed away from us, they sometimes imagine a privileged seat on the explosion, but pick any galaxy far enough from local gravitational tussles and it will report the same pattern. Neighbors bound in groups, a web of filaments nearby, and beyond that, a uniform Hubble flow in which recession grows with distance, so we are not special. When people ask why the night sky isn't blinding if space has no edge, they stumble upon a classic paradox answered by time. Expansion and evolution. Stars are finite-lived. The universe has a finite age since it became transparent, and the stretching of space saps energy from ancient light so that darkness survives. When people wonder whether we could ever reach an edge by voyaging long enough, they run into the reality of horizons in an accelerating cosmos. If the expansion keeps speeding up, there will be regions whose present light will never arrive here. And that future event horizon is a statement about the tempo of growth, not about a cliff in space. Even the fainter symmetry we do see, the slightly brighter microwave glow in one direction and dimmer in the opposite, is not a bruise in the universe's fabric, but a Doppler effect from our own motion through the cosmic rest frame, a local wrinkle that vanishes when translated into a frame that rides the average expansion. Philosophically, the centerless, edgeless view is not an argument that the universe is simple. It plainly is not at human scales, but an argument that simplicity reappears when you step back far enough, and that our oldest desire to find a privileged perch is better replaced by a discipline of coordinates and clocks that respect what we can test. Practically, this view matters because it underwrites how we convert redshifts to distances, how we draw light cones on spacetime diagrams to plan surveys, how we turn angled smudges of background galaxies into maps of intervening mass through lensing, and how we calibrate the ladder of standard candles and rulers that translates the sky's two-dimensional scatter into a three-dimensional history. It also guides how we ask questions wisely. Instead of demanding to know the center's location, which the model says does not exist, we ask how the expansion rate has changed with time, which we can infer. Instead of worrying about falling off an edge, which the model forbids, we measure how close to flat space is and how topology might reveal itself in repeated patterns. And instead of confusing the horizon of our sight with the boundary of existence, we keep our claims modest, knowing that the part we can see, vast as it is, could be only a patch. There is finally a humane comfort in letting go of edges and centers. It makes your backyard as honest a vantage as any high mountain. Everywhere is as central as any other for reading the large-scale story, and it invites a kind of scientific citizenship in which meaning comes not from standing at the universe's heart, but from learning to translate between perspectives. So the next time you look up and feel the tug to pick a middle, remember that in an expanding, nearly homogeneous cosmos, each calm observer writes the same narrative from their seat. Neighbors drift with them on small bound islands. The deep sea of galaxies slides away proportionally with distance, and no throne marks the origin. Not because the universe hides it, but because the question "where is the center?" folds when space itself is the thing that grows, leaving you not lost but liberated to map, measure, and marvel from wherever you happen to be. Reality might be computation-shaped. What? If the fabric you move through is less like a sheet you lay on and more like a code that corrects its own mistakes as it runs, an architecture where information is woven so redundantly that local damage doesn't spoil the larger picture, and where geometry itself might be the visible shadow of deeper patterns of computation. Start gently with an everyday anchor. Your phone keeps your photos safe by copying bits across drives, so a failure in one place doesn't destroy the image. And quantum engineers go further with error-correcting codes that spread a fragile quantum state across many physical qubits so that small glitches can be detected and reversed without reading the secret itself. Now translate that intuition to physics at its most extreme. Near black holes, where gravity and quantum theory must both be true, researchers notice that the way information hides and reappears looks eerily like a powerful error-correcting code. What happens in the bulk, the interior of a region with gravity, can be reconstructed from many different choices of its boundary data, and the same bulk bit is recoverable from overlapping boundary patches, as if reality had built-in redundancy. This is the essence of holography's bold claim. A region with gravity can be fully described by a theory defined on its edge without gravity, and the relationship between interior and boundary is not a simple dictionary, but a code that protects bulk information from small boundary errors. Toy models make this tangible without math. In a simple holographic code, you replace one logical qubit with a small web of physical qubits arranged like a honeycomb, and many different sets of those qubits can recover the logical one. Lose a handful, and the message survives, while the geometry of how the web is connected looks like a curved, negatively bent space. That looks like is not cosmetic. The number of links and their arrangement determines distances and areas the way a mesh defines a surface. And when you calculate how much entanglement, non-classical correlation, sits between two boundary regions, the answer tracks the size of a minimal bit-cutting surface through the web. A parallel to how in gravity, the area of a minimal surface tells you about entanglement across a spatial split. Read in this light, geometry is not a stage where information performs. It is the performance's footprint. Entanglement patterns knit together into something we perceive as shape. And when entanglement changes, shape shifts. Black holes sharpen the story by adding dynamics. They mix incoming information rapidly, scrambling, so that no small part of the boundary alone can decode it. But the whole boundary can, later, and recent calculations that reconcile Hawking's evaporation puzzle show a recovery curve that rises and then falls in a way consistent with unitarity, if you assume the right kind of coding built into spacetime. Computational ideas keep popping up where gravity gets tricky. The growth of a black hole's interior after it forms seems to mirror the growth of computational complexity in the boundary description, as if how large the inside feels tracks how many simple steps you'd need to reconstruct the state, and proposals with names like complexity equals volume or complexity equals action try to make that parallel precise. Even away from horizons, the circuit viewpoint pays rent. You can think of a quantum field evolving in time as layers of a circuit laid down like sediment, each layer composing small local gates into larger patterns. And network ansets are used by condensed matter physicists to approximate ground states, layered structures that focus detail at small scales and summary at large, double as maps of curved spaces when drawn just right, suggesting that efficient compression and emergent geometry are two sides of the same coin. If this still sounds like an engineer's dream projected onto nature, remember how much is already explained by it that used to be mysterious. Sub-region duality. The fact that multiple, partially overlapping boundary regions can reconstruct the same bulk patch falls out naturally from error correction. The apparent paradox of how bulk operators can be in two places at once on the boundary dissolves, because in a code the same logical bit has many physical representatives, and the resilience of space-time to small disturbances. Why local noise doesn't wreck distant structure reads as code distance. You have to flip a lot before the logical content changes. This computational lens does not mean the world runs on lines of software the way a laptop does, or that the universe is secretly a cellular automaton with rigid pixels. Those are stronger claims than the evidence supports. But it does suggest that the cleanest way to talk about what physics preserves and what it discards is in terms of information flow, redundancy, and recoverability, and that the best ontologies are the ones that make those flows explicit. Hints arrive from the lab in small, faithful imitations. Tabletop quantum simulators can build chaotic many-body systems and probe how quickly they spread information by measuring out-of-time order signals, a mouthful that you can translate as how fast a tiny change infects the whole, and the rates line up with bounds derived from black hole thought experiments. Programmable processors implement toy holographic codes and show in practice how a logical operator can be reconstructed from many different subsets, concretizing the bulk boundary flexibility in a chip. And materials with topological order, systems whose low energy behavior is protected by global features rather than local details, give us a controlled, non-gravitational setting where error correction and emergent gauge fields are literally the same phenomenon. A reminder that code as law is already true in some corners of nature. If reality really is computation-shaped, the implications are both practical and philosophical. On the practical side, it would mean our best strategies for building stable quantum technologies are not a technological add-on, but a rhyme with how the universe guards its deepest degrees of freedom, make information non-local, make it reconstructible in many ways, and errors shrink to nuisances rather than catastrophes. On the philosophical side, it reframes old questions. Where is a particle? Where is the inside of a black hole? As the wrong kind of queries, replacing them with operational ones. Which boundary measurements reconstruct this bulk feature? How many simple steps separate these states? And it shifts truth testing from metaphysical pictures to coding theorems you can try to falsify. Skepticism belongs in the kit. Holography is sharply formulated in special spacetimes and only approximate in our own. Millions of moving parts separate a toy code from full gravity, and the word computation is dangerously elastic. But the research program earns its keep by turning poetry into math. It writes down codes that exhibit the precise redundancy bulk physics demands. It derives inequalities that tie areas to entanglement that real data respect. It predicts recovery thresholds that match the best of possible worlds behavior we see in black hole models. And it pushes us to ask for experiments that catch information flow in the act of imitating gravitational logic. Perhaps the gentlest way to hold the idea is this. The universe does not have to be a computer for computational structure to be the right language to describe its most resilient features, just as you don't have to be a poem for rhythm to be the right description of your stride. And if you want a closing image to carry forward, imagine space-time not as a sheet to be torn, but as a tapestry of interlocking checksums. Pull on a thread and the pattern resists. Snip a small patch and the picture repairs itself from context. Stretch the cloth and the underlying weave dictates how it yields. Then notice that this is exactly the sort of fabric you would want if the goal were to keep meaning intact in a noisy world. Error correcting by design, predictive by compression, and deep enough that, when you lean in, you can see not lines of code but the quiet logic of a reality that safeguards its own story.